Good morning, everybody. So I'm just introducing the persons that you will see this morning. Jacopo Pasotti is a scientific journalist. He will be the moderator of most of the sessions. As you see in the board there, Neva Chieregato will design our conference through scribing, so you'll see her during the day designing us. And then I leave the floor to Laura Panzera that will open. And then Notarangelo will not be with us this morning, but Polignano will substitute him later. So we will get back his speech later. And we start with Laura.
Thank you. Good morning. I'm Laura Panzera, the Administrative Director of CMCC. And on behalf of CMCC, and especially of the President of CMCC, Antonio Navarra, who is not here today, I would like to welcome everybody to Lecce. The conference on safer transport in the Mediterranean Sea has been organized by the Ocean Lab of CMCC as part of the Ionio project. But as you know, it is also one of the events of the European Maritime Days. CMCC is a non-profit research organization established in 2005 with the financial support of the Italian Ministry for Education, University and Research. CMCC manages and promotes scientific and applied activities in the field of international climate change and variability research. The mission of CMCC is to investigate and model Earth's climate system and its interactions with society in order to provide reliable scientific results to stimulate sustainable growth and develop science-driven adaptation and mitigation policies. CMCC includes experienced scientists, economists, and technicians working together in order to provide full analysis of climate impacts on various systems, such as agriculture, ecosystems, coasts, water resources, health, economics. CMCC also aims to support policymakers in setting and assessing costs of mitigation and adaptation policies. CMCC is a national network. We have many offices in different towns in Italy, like Milano, Bologna, Viterbo, Capua, Sassari. In Lecce, there is the headquarters, the supercomputing center, and the scientific division of scientific computation and operation, and the Ocean Lab, who was started up about 2 years ago. CMCC has also a substantial amount of international cooperation with the research institutions operating in the same sector, like, for example, in the USA, NCAR, the National Center for Atmospheric Research, and Princeton University, the Yale University, but also with the Indian Institute of Tropical Meteorology, the National Marine Environment Forecasting Center in China, the University of Adelaide in Australia, and Tel Aviv University. The scientific staff of CMCC is composed of around 200 people, 43 of which have a PhD. 66% are younger than 40, and only 9% of these people are over 50. Thus, these numbers make CMCC a very young research organization. Supercomputing is at the core of CMCC activities. These activities are in fact based on numerical modeling solutions and methods. CMCC operates its own supercomputing center in Lecce, whose facilities have been ranked since 2008 among the 500 most powerful supercomputing systems in the world. The CMCC Supercomputing Center includes 2 IBM parallel systems, Athena and Calypso, for a total peak performance of 178 teraflops and about 9,000 cores. Thanks to Athena, which is the new parallel system we purchased about 2 years ago, the supercomputing center of CMCC is the third most powerful computational facility in Italy, the first completely dedicated to the climate research. The CMCC Research Network is distributed among 6 research divisions, which share different knowledge and skills in the field of climate science. You can find the details of these divisions on our website. Giovanni Coppini, who is the team leader of the Ocean Lab in Lecce, will provide you with more details on its activities and activities of the Ocean Lab. And he's also available for over the next 2 days for those of you who want to visit the Ocean Lab and its operational room. Just before leaving you, I would like to add just that Lecce is also very well known, not only for the Ocean Lab and CMCC, but also for the Baroque architecture and for its delicious food. I hope you will enjoy your stay in Lecce.
Thank you very much, Ms. Pansera. So I think we have now to go farther because we are already a little bit in late with our program. So next is coming Professor Alan Bloomberg from New York. He will introduce himself shortly, and he has half an hour to explain us many things he has been studying there. Then he will be followed by Paolo Oddo and Giovanni Coppini from the CMCC, and then Samuel Javigna, I hope I pronounced it correctly at least, from the IMSA from Portugal. So please, Mr. Bloomberg, take.
Can you hear me with this? My name is Alan Blumberg. I'm a professor of ocean engineering at Stevens Institute of Technology. I'm very pleased to be here. I have many good friends in the audience, and I'm happy to be here to talk to you about ocean observing and prediction systems. What I want to do is to tell you why we do it, and then how. And the why is really important because that allows you to bring in more funding and more stakeholders, people interested in the system. This is the region where we have our observing and prediction system, New York City. And you can see the land is blue, not brown, because we had a big flood from a hurricane. And since this Hurricane Sandy came to our region 2 years ago, the amount of money for research has been huge. So we're trying to figure out how to spend the money and develop technology that could take you many, many distances into the future. So why do we do this? This is a very famous case. This airplane crashed in the Hudson River maybe 3 years ago, and you see all the people on the wings, and everyone says the pilot saved everybody. And you know what I say? Ocean observing saved everybody. Because when I saw this airplane, everybody was on the wing. But they said, now what do we do? How do we get from the airplane to the land? And that is when ocean observing and prediction became important. We knew which way the water was flowing, how fast, so we knew where to put all the ambulances and all the emergency management people. Number 2 is we had many episodes on the beach where you go out to the water and there's syringes and all kind of medical waste on the beach. So what we do is figure out where it came from. So you backtrack. Important example. Another case is a barge caught on fire and exploded. People in the water, you have to get them out of the water. And number 2, you have to figure out where the oil goes from this barge. Another example is this Norwegian cruise liner coming into New York Harbor right by my university, stuck, not moving. So the captain calls me up and says, the current is much too fast. We can't come into the port. How long will the current be fast? So I say, how do you know me? How do you know to call me? He says, oh, we know things. So it's important to figure out who comes to your website to use the information. So here's the captain of the ship with 6,000 people to call me to say, when will the current stop so he can go into the port? And I have another case. This hurricane came and produced amount of water from the floor to that camera of water that came into my university town. And the question was, how do you know that ahead of time? And this is what happened. This boat was in the water, came on the land. And this is a picture of me saying, my boat. This is our system. It's called the New York Harbor Observing and Prediction System, NIHOPS. It goes from the land. It goes from the land. This is New Jersey and Long Island. New York City is here. It goes 100 kilometers offshore and 400 kilometers alongshore. The domain ends at the continental shelf break, and it goes from a resolution here of about 5 kilometers to 10 meters inside. And I want to emphasize that all the people that you are trying to save in this world and protect are on the land. They're not out here far away. And early in my career, I was doing modeling way out here, waves and currents. But then I realized how many people really care. Some navigation care, but most of the people who I'm interested in live on the land. So the higher resolution near the land is important. Our job in my system is to observe the environment, to predict it, and then to communicate this information to the public. Each one of these is very difficult. But if you don't do them all, then you really don't get very far. We have been very fortunate to have instrumentation all along the waters of New York and New Jersey. These are some examples of what we have. We have our own buoys at various places. We have U.S. Coast Guard buoys, where here is hard to see with this light, but we have ADCPs on U.S. Coast Guard buoys. You will see a little later that my buoys get destroyed. Ships hit it. People shoot at it. Everything like that. But these buoys, nobody touches because that's owned by the government. So people are much more cautious when it comes to the government buoy. We have sensors like this here, measuring temperature, salinity, water level, many places. And all this data comes in real time into our system. We also have HF radar system set up. And this is along the coast where we get a good view of surface currents. And first of all, you take this data and you put it on the website so people can understand what's happening every hour, and then you could ingest it into numerical models to get better and better nowcasts so that you can forecast better into the future. We also have mobile sensors. All the fixed sensors that you know about are located here or here, but what happens in between? That's sometimes very difficult and to understand. So we have like a sailboat like this that the tourists use every day. And in the center board of the sailboat, I have a CTD that measures salinity and temperature and turbidity as the ship moves. So we get a position in New York Harbor, and we get, for example, temperature. This is salinity, surface salinity, color-coded. Everywhere that boat moves, we have a record of what's happening. And you can see that the salinity varies tremendously, over 5 kilometers. And that is because there's a fresh water here source and very salt water here. So it's important to know what's happening in between your fixed sensors. We have research now to figure out how do you use this data in a model, because it changes as the boat moves. So you have to figure out how to put that into your data simulation system. It is very hard to observe in a coastal ocean. I know many of you know that. This is what happens to our buoy. One night, a ship runs over it, and there goes all my hard-earned instrumentation that's on the buoy. In the coastal waters, we have biofouling, ship collision, we have ice. We have people very curious about the sensor. The fishermen tie up to the buoy and go fishing there. And they move the buoy from its position. The scales are very interesting. Scales and geometry, things change very quickly from place to place in the coastal ocean. So you need to have many sensors. And there are a few operational sensors. We can measure temperature, salinity, DO, turbidity, but we can't measure phytoplankton and various chemicals. So we have to learn how to do that too. Our modeling system really is threefold. We have a very large-scale grid here that does a lot of the North Atlantic, and then we narrow down to our NIHOPS domain that I showed you before, and then we zoom into our New York Harbor region. And that is this picture here, high resolution. My university is located right here, and this is Manhattan. So you can see we have a very special place to observe what's going on. The Norwegian cruise liner that I showed you, it comes out here from Bermuda, comes into the waters of New York and New Jersey, and it comes up this river, and it wants to dock right here. So it has a lot of different oceanography to navigate. So we have a triply dimensioned system. We use the Princeton Ocean Model, and if you're interested, we have a lot of new innovations that we could pass along to you. But I'm not going to go through all these. Our system really is totally automated, so that every night at midnight, we go back 24 hours in time and bring in all the data that we can find, and then we integrate forward 24 hours, and then we forecast 72 hours into the future. And I do it in a way so that I don't have to do it every midnight. I don't have to push the button. It's automated. And it's automated so that we can have a system with the models at the heart, but we have observed data coming in. We have external model data, for example, forecasts of river flow, of precipitation. So that's external data, feeds into the model, and out comes various information that we put on the website and we send to various agencies. The modeling system, the heart of it, is of course hydrodynamics. There are pieces of atmospheric heat flux modules, surface waves, data simulation key, water quality, and sediment transport. The heart is the Princeton Ocean Model here, which gives us the currents, temperature, salinities, the basis for all the other kind of models. In order to make the model work really correctly, you have to have high-level information. For example, in our system, we have inflows from 93 major rivers. So we have to be able to get that data into our system. We have data from 146 minor ungauged river systems. If you don't have this in, if I don't have the amount of fresh water coming into a certain region and I live in that region, then I can't predict that region. And the person who's observing that region says, your system is terrible because you don't match where I am. So the amount of attention you pay to detail is key. The more detail, the better. And then in our system, such a large metropolitan region, we have many, many sewage treatment plants. And what does the sewage treatment plant do? It discharges fresh water out into the marine environment. So you need to know how much fresh water. And also, we have 39 power plants. And what does a power plant do? It brings in water from the estuary or river or the coastal ocean. It heats it up to cool the power system and then discharges it very hot. So you need to have all those pieces in order to get a good prediction. So we have 39 power plants. How do we have so many of these in our model? I have a lot of graduate students. And their job is get the numbers every day. And if you're wrong, you don't graduate. That's what I tell them. No. One of the keys is validation. People always ask me, how well are you doing? How do you know if you're doing well? Well, we have many instruments sending in data in real time. So on our website, we would make plots like this. Here's time, and this is water level in the vertical in meters. 0 to 4 meters, 0 to -4. And then we put out our forecast here, -24 to 0, and then in time, the data is in red dots. So this way you get a sense of how well we're doing every particular day that you're interested in. So a lot of attention to validations is part of our system. So here is our website. So when you come into this website, you can immediately get a sense of what we have. And I'm going to show you a little bit about that. The web address is down here. So if you're bored later today, after my talk, of course, then you could Google this address. Stevens.edu, Maritime Forecast, one word. The message needs to be clear. This is a message that came from our government, the National Hurricane Center, during a hurricane itself. The government puts out bulletins and advisories of what's coming in the future. And what they said at the end of this event, when they did one of their reconnaissance, they said, New York City Office of Emergency Management uses the Stevens Institute of Technology Storm Surge interface because it is cleaner and requires fewer mouse strokes to navigate. So I said, wow, good. That enables people to come to see what you have to present to them. If they can't figure out the website, you know what they're going to do? They're going to call you. And I said, don't call me. I said, just figure it out on your own. And hopefully the website is done in a way that you don't need to call the scientists who put the information there. But this is a key. If we are fabulous in terms of observing and forecasting and nobody knows, then it doesn't help a lot except for us. The public won't be able to use it. So the message is the key, and that should be clear. We also have apps that sailors who are interested in winning the sailboat race, they have the app on their phones to know which way the current is going. Now you say sailboat is about the wind, blowing your sailboat, but sailboat racers are very competitive. So if they know the currents, then they have a big advantage. So they have an app with the surface currents, which way they're going and how they change. And this is currents in one direction and another direction over time. My biggest fans, if I could call them that, are the sailboat racers and the kayakers, because they want to know exactly, minute by minute, what's happening in the water. This is our storm surge warning system that has brought us a lot of acclaim during this last Hurricane Sandy. These are the amount of sensors we have that measure water level along the coast of New York and New Jersey and all the way up the Hudson River. These are sensors that measure water level. Data comes in real time. When things are normal, is green, normal levels, those boxes are green. But when an event is coming, they turn colors. They turn red, you can see, which is a moderate flood. They go to purple, which is major flood, and they start to blink, right? And then the minute you get into the near flood, the yellows, emails go out to whoever has signed up for the system. It was originally paid for by New Jersey State Police. And the police wanted to know when there's a big event coming to the beaches of New Jersey, they want to know when they should move the people out. So that's how we started with this system. So these green boxes would change color, they'd start to blink, and then they would send emails out to the respective people. During Hurricane Sandy, we were forecasting 2.5 days before the event came to our area. The government did it 2 days ahead. So university, we could take chances because we can change minute to minute. The government computers and methodology are very slow to change. So we can change bathymetry, we can change winds, we can change everything fast, very fast, where the government can't do it, and that is why we can put a forecast out 2.5 days ahead of time. And what we showed during this particular hurricane was that along the coast of New York and New Jersey, we were within 5% of the surge, and that surge was 14 feet, about 3.5 meters of water that came into the system. In New York City, we were low by 20%. And that wasn't good because we're right in New York City, my university. And then the rest of the area was low by 10%. So we were typically low. So we didn't get the peak of this at all. And we're trying to figure out why. Why were we low? Well, it turns out that when we do our forecast system, during the data gathering, we use winds from the National Weather Service. in the United States. This is a 16-kilometer model that's run every 6 hours, the best. And we realized that if there are errors in the wind field and pressure, guess what? The water knows those errors. And the water is very sensitive to the wind field, more sensitive than you could imagine. So what we have done as a test case on this plot, this is time, and this is elevation in meters, is to use data, wind data, from different forecast models, from Rutgers University, from Penn State University, people who really do good jobs in this. And you could see that the water level from this hurricane, the hurricane actually came on the 29th at very late at night, right in here, and you could see that the maximum varies tremendously depending on which wind field that you want to use. So our next piece of research that we're doing now is to bring in 5 or 6 different wind fields. But you know what that means? You have to bring in the data, and then you have to run all these computer models. So instead of running 1, now we run 5, maybe 10, depending on what's going on. So it needs a lot more computer power than we've been using before. So the message is the peak is highly dependent on the wind field. I say that the ocean knows the correct wind because you have to predict the water level at your spot. And that is only from the correct wind. If you use the correct wind, this is a comparison you get at many different stations around the area. Red is observed, the blue is modeled, and you can see they're right on. There's very little air, 16 centimeters RMS air. So if you know the winds, and this was done a year after the hurricane, using a really good analysis of the winds by Ocean Weather Incorporated, we were able to predict it pretty well. So the message is we need better atmospheric forecasts. I want to tell you a story about what happened in my university during that hurricane and where our research is going. We have developed this Princeton Ocean model, the ocean model, and we've moved it from the ocean to the coastal ocean, to the estuary, and now on land. So we have a really good flooding and drying algorithm that I want to show you. So this is my university town. My university is right here. New York City is right here, 2 kilometers away, across the water, right? And this Hurricane Sandy came, and this is a time series of Hurricane Sandy. It was high water, then low water, high, low, and then the hurricane hit here on the 29th about 9 o'clock at night, 9:30 at night. And I'm going to show you how the flooding occurred in my town. Everyone says, look out. If you live along the water, this is the water here, you have to be very careful. And we have to figure out how to stop the water from flooding here. And I said, don't be so sure. Let's see how the water came in. So this is an animation using particular colors. Blue is 0 to 3 feet, then yellow, then orange, and then red. And red is 9 feet of water coming into an area. So this is the high tide of the morning of Sandy. Already you get a little flooding here, a little flooding here. Now it came low tide, and everybody said, oh, forget it, you're wrong. I said, well, here comes high tide, and here comes the hurricane, and watch how the water comes in the streets. See how it goes in the streets? And yellow is 6 feet of water. Red up here is 9 feet of water. By using this model, I have 3-meter resolution for this town, right? And you're able to see how the water is in every street here? No water here. So the water did not come this way. It came on the south and to the north. Before I made this animation, people always thought, oh, the water's going to come, right across this direction. I say no. The water came in from the top and bottom, and look, it got stuck in the back. And the back is very low. So once the water gets there, it can't leave. So this is a picture that shows the maximum water that came into the town. This area right here has a very large train station that takes people into New York City and back. And there was a lot of taxi cabs here waiting for people. And the taxi cab company said, oh, I understand a lot of water is going to be coming in, so let's move the taxi cabs. So they moved the taxi cabs, guess where? Right here. Worse. Right? And this is what happened. Very famous picture. All the taxi cabs were moved to a safe location. Is this a safe location? No. And my message was not clear. The taxi cab company didn't know that I'm making these predictions. They know now, right? So getting your message out clearly is a key. And people ask me, how do you know? How do you know you're right forecasting water on the land? I said, well, good question. What I did is I went to my town, it is 2 kilometers on a side, and said, send me pictures that you took during the hurricane. Everybody has cell phone. Send me your pictures so I can see how much water was there. So this is a typical example. This is a picture that I know the location, I know how much water is there, and I know the time. See the time here on the clock. So I could use that as a data point. When I made this announcement in my town, I had thousands of pictures, but most weren't very good because the hurricane came at night and it was dark and people were scared. So they took pictures that didn't help me very much. And the second thing that was even worse, they didn't know how to take it off their cell phone and give it to me. So we have to educate everybody how to do everything. And when you go out and get data from this town, which is 2 kilometers on a side, these are all the data points that we could come up with, maybe 60. And we plot them hindcast of water level over the ground versus observed water level over the ground. And I said, pretty good, we were pretty good. And I'm writing this up now for publication to give you a sense of how you do this problem from the ocean, from the coast to the land. This is the message I want to do during the next hurricane. Have you ever seen this movie, The Day After Tomorrow? It was about climate cooling. And the earth became all ice. And sea level rose very high and flooded New York City. So when the next hurricane comes, or a storm, a nor'easter, I want to make a movie like this ahead of time and show it to everybody and say, you decide if you want to leave or not. I don't have to convince you. The government doesn't have to convince you. You decide if you live right here and you see this, you may decide to evacuate. So my conclusions are, in order to do anything in the marine environment, we need more observations. We have lots of observations. We have 200 stations around the area. Is that enough? No. There are many big gaps that we don't cover. So we need mobile sensors, HF radar, tide gauges, drifters, gliders, etc. We need to spend time learning about ensembles, meteorological forecasts. They vary substantially. Our weather service does ensemble modeling. They run 10 different wind fields and they average them together and they have one. I said, that's not ensemble modeling. Why don't you weigh them by which one is the best? They haven't done that yet. So we have to figure out how to do that. And then we need much new research. We have to understand the physics and modeling of how flooding occurs, how every street is different, how the coastal ocean interacts with the street, and how that happens. We have to use our expertise to get out the best forecast we can get out. And finally, we have to be able to explain them to the general public. When the press calls, you have to be able to talk to them because they're your best ambassadors. They will put an article in the newspaper that talks about what you do, and if you speak, that's it. You're not going to be in the newspaper or on television. So it's important, especially young people, practice communicating. That is the key to good science. So we do ocean modeling and forecasting for a whole lot of issues. I'm Alan Blumberg. Email me, call me, etc. In order to make this work, we have a lot of partners. I don't have one person that funds us. I have many, many. So if one funding agency stops, I go to another one. So it's important to have many people that fund you at the same time, so you don't depend on one person as you go. Thank you very much.
Thank you very much. Thank you very much, Alan. I think we proceed further, or shall we have time for a short question? Good. So we have time for one question. If you don't have any, I have plenty. I am a journalist. I am quite ignorant about this subject, so that's why you probably choose me. So that if you impress me, if you make things clear to me, then you are sure halfway on making things clear to most of the public. But I would like to hear some question. If you have one, just one question, please.
Thank you very much. So I'm Slim Ghana from Tunisia. So you show us many, let's say, extreme events with flooding and, but could you tell us what are the solutions that you are offering to your clients or founder? Is it possible for you to give us some example of what are the decision making that you are helping with your tools?
Good question. So we do all this work to observe and predict the environment. Most of our research is not to do this. It's to answer a different question about the physics of estuaries, about the physics of the coastal ocean, and we put all that information together to make this system. Being a university, we have to be very careful of the words we use to talk about this. Is it decision support? Is it guidance? Is it awareness? There's all these words that you have to be careful with because they involve liability. If you make a forecast and it's wrong, my university president says, we don't want to be sued. So when I say that this is awareness system, or it is a decision support, but you make the decision. We don't make the decision for you. So we put all this information, and the people decide what they want to do. It is very different than me deciding what they should do. If I were a company, then I would take that risk. But so the university doesn't want to take the risk. So the university says, this is a guidance. Here's all this information. How good is it? Here's how good it is. Here's the uncertainty. Here's the risk. You decide. So decision support is important to get that message across.
Thank you. And as a citizen, I think my first take would be like that I'd like living in New York City now, because it must be the safest coastal town in the world.
Almost.
So
I need more research.
The question I'd like to do, but I don't know if we have time, is like, is this exportable? Are there any other towns so safe as New York City in the United States and maybe in the world, or is it unique?
Well, I think New York is among the leaders. But New Orleans has a lot now. They're coming up. Many universities are starting to do regional applications along the east coast of the United States. So more and more as it's coming. The climate is changing. Storms of the future are going to be stronger. So we have to be ready in the United States. It doesn't help you to be ready after the event. So you have to do it now.
Thank you, Alan.
The most important thing I want to talk to you about as I close is the word yes. I believe in the power of yes. So if somebody says, can you come to my museum on Sunday morning and give a talk about your forecast system, I say yes. If good friend says come to Italy to talk about it, I say yes. You know why? Only good things can happen from yes. If I said no, we would not have a discussion. We wouldn't get to know each other. And that's what I tell my students. Yes. You say yes. Thank you.
Message. Thank you very much. Thank you very much. I leave now the floor to Paolo Oddo. Thank you very much. You have 20 minutes.
Yeah. So and then I have been asked, would you like to give a talk just after Professor Bloomberg? I say yes. And I was wrong. I mean, that's clear. Now it's absolutely clear. It's quite embarrassing for me. Thank you again for your fantastic talk. On one side, for me now, it's going to be very difficult to provide this talk, followed after Professor Bloomberg. On the other side, most of the concepts that Professor Bloomberg has shown are shared clearly between mine and his talk, so it's going to be much easier for me to, I think it's fine. Okay, good. So on the other hand, I was saying before, I mean, most of the concept that has been tackled by Professor Bloomberg, I shared with my talk. So it's going to be much easier for me and also much easier for you to understand the message I want to pass you. So here is the title of my talk. I don't know how much it matched with the content. However, is the operational oceanography for situational sea awareness from global to coastal scale, or we can also imagine from observation to applications. So I will briefly introduce you what is the challenge that we face that has been clearly explained by Professor Bloomberg, and then two examples, one which is active at European level, which is the Copernicus Marine Service, and the other one that is just an example that is provided by the Ionio project, who is supporting this conference. And then we cover the entire stream from the observation to the application to conclude. So what is the challenge? As we have seen just from the talk before, that the effective management of and protection of the marine environment must be science-based. I mean, we know, unfortunately, based on our previous experience, if we try to manage, protect, and use the marine environment without knowing how it works, that can be a disaster. And the challenge is that we know that there are interdisciplinary processes coupling physical, biological, chemical, sedimentological, acoustical, and probably other aspects that we know are occurring on multiple and interactive scale in space and time with bidirectional feedbacks. So the marine environment is very complex. We have the physics that is interacts at different scale, different times. They interact with biology, with chemistry, with sediments, with acoustic, and that make the understanding and the modeling and the prediction in the ocean environment very, very complicated. So it is a challenging for the research, and at the same time the research must provide some information to the decision maker. So with this general purpose in mind, several programs have been established to promote, facilitate research and application in interdisciplinary global, coastal and shelf ocean science and technology in order to increase the scientific understanding of the ocean process. So while we are still increasing our understanding on the ocean processes, we are already started to provide information, as Professor Bloomberg has showed you before. And so what is the answer to this challenge? The answer is provided by the operational oceanography. You can find several definitions of operational oceanography if you check in the web, in the literature, but most of these cases all suggest that the concept include the systematic observation of the ocean, you have seen before, and the use of the data in scientifically derived application. such that timely information is made available to the decision making. And this is the process that we have seen exactly before. So from the observation to the information to the decision maker, and those processes must occur in a given time that the information is still useful. And the operational oceanography rely on the concept of ocean observing and prediction system. The concept of ocean observing and prediction system for field and parameter estimation has been crystallized at least with 4 major components. So we must have an observational network, a suite of platform and sensors for specific tasks, multidisciplinary, observing the ocean or the water, let's say more in general, in all the aspects, from a physical, biological, sedimentological, acoustical point of view. Then we need a suite of interdisciplinary dynamical models that are used to forecast, to fill the gap between the observations through the data assimilation scheme, that also in this case must be able to merge and digest all the information and put together in the model. And then, as you have seen before, that's why I'm saying my talk is much easier now after Professor Bloomberg, we need to have an information and dissemination tool. So without this last bullet, all the previous effort remain confined in the science, and this doesn't reach the community. So those 4 are the components of the ocean observing and prediction system, which is the core component of the operational oceanography. And we have seen also that all the systems must be modular, based on distributed information, providing shareable, scalable, and flexible and efficient workflow management. So this is the challenge, and through the information we are able to gather and provide and elaborate, those are the domain of the activities of the operational oceanography. So from marine resources, species, stockfish, marine safety in case of incident, oil spill, accidental or not accidental, coastal and marine environment, we have energy, beaches, we maybe have harbor or climate and seasonal forecast, ice, CO2 concentration, global warming, and so you can see how wide is the range of spatial and temporal scale that the operational oceanography has to cover. And it is not so easy to provide information at all these scales with the given accuracy, an accuracy that makes this information really useful. In Europe, this concept has been consolidated in past year thanks to this sketch. This sketch is summarizing all the process that we need to address with the operational oceanography. Here we have in the left side, we have the observation that can be from satellite, can be from in situ. Then we can have other data sources. In this case, those are the GMES or the now Copernicus data. These information are integrated thanks to the model. There is a quality control, they are formatted in the same way, and they are organized. And thanks to the model, they are then provided in a common interface. And so we have fulfilled half of our commitments, and from this information then we can create, here we have the intermediate user, we can create downstream services with maybe additional data in order to arrive to the end user, and so the information which is really useful for the end user. So the operational oceanography, in order to be really useful, should cover this entire stream. What I'm going to show you that we can see that in Copernicus, so at European level, we have project, we have the Copernicus Marine Services that is covering this area. So it starts from the observation that they are taken from the Copernicus, plus additional information, and then thanks to a suite of models, data simulation scheme, and also tools for processing the data, then provide this information in a uniform way to the intermediate user. And then we will see later how to fill this second part of the what they call butterfly, because here they say 2 wings. And we are now in the middle of these two. So what is the Copernicus service? The Copernicus Marine Service is a service providing information on the state of the ocean and regional seas. How? Through an infrastructure built and provided by MyOcean and MyOcean 2 EU-funded project. How do we reach this condition? through the experience of more than 10 years. So what has done the European community has consolidated the past experience and expertise in pre-operational ocean monitoring and forecasting capacity in Europe that has been developed through precursor European projects. And here they are mentioned Merci, Bosphore-GMS, Marcos, Polar View, and then later MyOcean and MyOcean 2. And those is actually the project that are providing the Copernicus Marine Service. How, and that's again the concept that has been fantastically illustrated by Professor Bunge, how must be this service? Must be integrated because it's a system of systems. So we are covering all the European area and we are covering several disciplines. So it's a merge of different systems. It's open and free because in order to be useful, all services are available to any user freely. Is reliable, which is very important. So the quality and the availability of the product are continuously monitored. So you can see, you cannot just take the product, but also you can have also an estimate of what is the quality of the product. And the availability, that's again very important, because if we provide the information every day of the year, except that the day the information is really useful, that's all the exercise became without sense. And then also important, direct access to the data. So all these systems are integrated and they have a unique access point. And you can access direct request or count and direct response. And again, all these services, data, information are provided according a user-driven approach. So during the years, the past 10 years or maybe 15, there'd be a direct connection with the end user through fact sheet, questionnaire, workshop, and dedicated work package in the project in order to understand what are the user requirements and adapt these data to the user needs. So in order to have this data really useful for the intermediate users. How this information is provided? In the Copernicus, there is a web portal that you can access, is myocean.org, and you have a catalog, and the catalog is organized by region, and you can see that it's covering the entire globe. We have the global ocean, we have the Arctic, Baltic, Norway, the Western Shelf, EBM, Bay of Biscay, the Med Sea, the Black Sea, so you have different regions, and in each of these regions you have currents, you have temperature and salinity, surface wind, sea level, biogeochemistry data, sea ice were present, not in the Med, clearly, and those data are provided in different temporal and spatial scales. So for some management, maybe are useful the reanalysis, covering 10, 44, 45 years, or real time, or maybe the forecast for other applications. Okay, and again, the very similar to a slide that has been shown before, how we are able to provide this system, combining all these institutions and merging and making all the institutions collaborating in Europe. So you can see the effort which is required. Okay, and then now I skip very fast. Those are the products, for example, of the Mediterranean Sea. I go directly, since I am delayed, to the slide that summarizes. In the Mediterranean Sea, through the Copernicus, you can have analysis and forecast for the physics, for the biochemistry. You can have real-time in situ observation, real-time satellite for SST, for the altimetry. Then you can have delayed time, so with better accuracy, better quality, chlorophyll, attenuation coefficient, reflectance, or delayed mode in situ observation with quality control, reprocessed altimetry, or reanalysis for physics, Hindcast, or for the biogeochemistry. And this is a very nice application. So even if the butterfly, as I showed before, break in the middle, or just cover the first wing, then, thanks, here we have the Copernicus product. Here we have an intermediate user, that in this case was INGV. And here we have an end user that is an exercise that has been done in the case of the Costa Concordia incident that occurred 2 years ago. And the INGV was providing scenario of the possible spill of the oil, and then the Coast Guard was using this scenario in order to take the decision in support of the operation. So now if we want to arrive to the end user, so we want to cover the second wings of the butterfly, up to now this is left to project, and I want to show you the Ionio project. What is the concept? The Ionio is Interreg project in collaboration with CMCC, ENEA, and SCMR, a Greek partner. And the idea is to do the downscaling. So we have the Copernicus service, which is active, and now we want to focus on a specific area and want to reach the end users. And so what we do, we increase the observing system, we increase the forecasting system, and then we disseminate the information, and we reach the end user, 3 decision support system, search and rescue, ship routing, and hazard mapping. I'm going to run a little bit fast. So this is the Copernicus observation in the Med, and we have buoy, ship of opportunity, Argo flows, satellite, glider, and so on. And we increase the density of these observations in the area of interest, which is the Southern Adriatic and Northern Ionian Sea. Supporting existing buoy, that's very important because the support to the observation is very important. Deploying new buoys, 2 Argo float has been deployed, and improving the ship of opportunity crossing the area. So, and you see that we increased the observational coverage in this area. For the modeling point of view, again, we start from the Copernicus, and then to reach the right scale, we do a downscaling approach. So we have models that cover the Central Mediterranean Sea, which is nested in the Copernicus. Then we go with zoom in the area, and we have additional model with higher resolution, but also providing information that are not provided by the Copernicus service, like the wave. And in some case, which is very important, in some case, we need also to change the modeling strategy. If we want to reach very, very high resolution coastal area, we move from the final difference model that has been shown before to the final talent model. This is a Schleifen-based model that you can see how it covers now the coastal area, and you can see here the Gulf of Taranto with a resolution which is not possible for the other model. We clearly disseminate this information. This is a web page. You can check the observation, what the observation available. You can visualize and download the observation. You can visualize the model results, wave for different region, and I think this is surface temperature. And I go fast, and you can see the difference between a standard product, the information that the standard product can provide you in the Gulf of Taranto, and the information of dedicated product that can provide you in the Gulf of Taranto. So we are now really reaching the scale that allows to provide information also for this kind of management. On the base of these environmental information from satellite in situ, different scale model, and additional data, then we created some decision support system. This is an example of pollution hazard mapping. So we have data about traffics or ship in this area, and we have done some simulation using all these data and oil spill model, and we created hazard map for the open ocean. Here you see all the area and the zoom, or for the coast. So more red is the area, higher is the hazard and the risk that you have pollution from oil. This is just an example, and this is will be provided to the web. We created also a ship routing and safety decision support system, again, taking the information that we had generated, and on demand, we can provide you a suggestion of what is the optimal route in terms of safety. So you see an example of a route, red one, without accounting for the weather condition, and the black one that account for the weather condition, in this case, is just the wave field, in order to avoid dangerous situation. And the last one that we are, we are developing is a search and rescue decision support system. So combining all the information we have created, again, so on demand, you give us through the web a position, the last known position of a body, also providing us information what kind of body it is, and then this system provides you area where the probability of finding the body after a given time is higher, and that's again can be very important. I want to conclude. Yes, we have seen that the Copernicus within the last year program has developed robust and reliable services, consolidating and continuous precursor activities, and now the service is provided by MyOcean. Through the production of these services, the Marine Corps services support many organizations, institutions in the public and private sector in all the activities, and the products are also the base in support of new research or application-oriented projects like the Ionio. And I want to also stress that the development of decision support system requires an active involvement of the stakeholder. Just conclude that everything is not finished, because there are still challenges that must be addressed, because the strong interdisciplinarity, multi-scale, multi-physics, natural and the marine environment is only partially understood and so modeled, and a lot of research is needed in this area. For example, the flow from small to large scale is still under investigation. Up to now, you have seen we start from the large scale and we reach the coast, but there are feedback from the coast to the large scale that up to now are not modeled and not in the operational system at all. And then the observing and prediction system are continuously under development as a consequence of the growing knowledge and technology. And this is very important, that we develop all the components from the observation, models, data simulation, and the dissemination tools simultaneously. And I think that's it. I would like just to thank Eleonora for all the effort.
Thank you, Paolo. Thank you very much. We are really running late now, but I think if you have a question, I'd like to anyway give the chance to Paolo to address your question. Just be short, both of you, please.
Thanks, Paolo, for your nice presentation. I would just link your presentation to the previous one made by Professor Bloomberg. Essentially, you're saying the main problem is related to the amount of data that are available. Do you hear me? Okay. Essentially, Professor Bloomberg was saying that the in-situ data are not enough, and this is true. At the same time, from an information point of view, there is a need to essentially manage a lot of data. In fact, we are speaking in this moment of data deluge. So there are so many data coming that have to be managed. They are mainly coming from satellites. But anyway, this is just the introduction to the question. So we are moving from a multi-platform observing system to observatories. So a lot of data would be collected in observatories. Radar are ones, but at the same time, gliders, ships, and so on. So in this case, the temporal and spatial resolution will be very high in certain areas. My question is, there could be limitation in a simulation of high resolution and spatial and temporal scales in model forecast?
Yeah, in theory, the oversampling can be a problem, in theory. So from a mathematical point of view, if we want to assimilate in the model an area which is oversampled, could be a problem. In practice, that's happened very rarely. I never experienced this fact in my life. Also because the resolution and the complexity of the model is growing as fast as the number of observations are arriving. So it's true that now with satellite and improved observing system, we are getting more and more information, but it's also true that now we are seeking to have operational model like Professor Bloomberg showed with 3 meter resolution, or 100-meter resolution in the case of the Ionio. And that's, so the ratio between the observed data and what is resolved by the model, I think that is more or less maintained. And thanks also to model development and the computer facilities. Now we can run model with a resolution that was totally unpredictable 10 years ago. But I think could be relevant.
Thank you, Paolo. And it's now time for you, Giovanni.
Dov'è la presentazione?
No, l'avevo già letta.
Era già la tua? Ecco, cerchiamo Mongoose. Servizio. Good morning again, and thanks a lot to Yeah. Can you hear me? Yeah. Thanks a lot for coming in Lecce for this conference. It's very important for us. So I tried to merge two different topics, let's say. One is Mongoose, is our network at the Mediterranean level, and one is our small laboratory at CMCC. I tried to, in this slide, I'm trying to pick up some of the aspects of operational oceanography. I believe that cooperation is very important together with innovation, and as Alan was saying, some scientific challenges also drive our activities, but then all the field of application will also push us. And so you have seen already similar slide, much more fascinating the one of Professor Bloomberg, but basically we work for safety of navigation, coastal protection, for instance from coastal erosion is one of the challenging topics. Search and rescue, we will have a session tomorrow together with a pollution emergency. We also have we think that is important also to support touristic activity because it's a very strong economic driver. Of course, we support military action and hopefully peaceful, and then application in the fishery, in the extraction of hydrocarbon, but also renewable energy. So many users. I mean, these applications that I've mentioned are answering to questions or to needs of many different users, from seaside tourists to offshore industry. So it's a very broad, and this is also challenging because then it means that you have to reach public that are on the beach at the same time using or transforming similar information in a different way. You could reach Coast Guard, so for very different topic. To give you an overview of a very broad coordination activity, we are a network, a worldwide network of GOOS Regional Alliance. It means that we all work at different level, at different maturity level, for managing the global ocean observing system and services. Specifically, as Paolo was mentioning, at the European level, we work in the framework of MyOcean, or we base our services on MyOcean. But at the Mediterranean level, we also are organized in a network, and I think this is important to express or to explain the cooperation. International cooperation is very important in this framework. We are many institutes, like 33 institutes, that try to do what? Try to improve the products, but also increase awareness on our products, increase the downstream by coordinating and implementing services. When we say downstream, I mean, most of you knows, but it's to go to the final users, and then, of course, work with to develop the system, so to transfer the system and develop together observing and forecasting system also for non-European countries. This is our website, mongoose.eu, and the coordination effort is huge because there are many ocean forecasting systems in the Mediterranean, up to 70. Of course, there is one basic for the Mediterranean, but then there is the downscaling approach that all us are working with. So we downscale toward the coastal areas, and also there are applications for storm surge, biogeochemical model, oil spill model, so different type of models, all coordinated. And then the in-situ observing system, more than almost 200 stations. We will have Antonio Novellino presenting EMODNet that is trying to support this coordination, but also not only buoys, but also other platforms, and then, of course, the remote sensing satellite measurements. This is a picture that shows you the partially the complexity of a downscaling system in the Mediterranean Sea, all coordinated, and we are running at Ocean Lab, as you will see later, the Adriatic forecasting system. As well, the in situ part is quite complex. This is just a few examples of buoys that release real-time data also through EMODnet that you will see later today. And another important activity that is done in the framework of MyOcean is the calibration validation. It means compare the model results with the in situ data. This is what MyOcean is doing for each single buoy you see as a yellow dot here. You can compare with many different forecasting systems, and for the users is very important. Even if this is still a bit scientific driven as a also way of presenting the results, but the concept is also very interesting for the users. EMODnet later will show you the observing system, but is coordinated with the mongoose as a challenge. This is some new data for ocean color within MyOcean mongoose, and of course application. Tomorrow Stratos will present us MEDES, is a product for oil spill forecasting system, and is of course relevant in the context of mongoose. Now, going briefly to Ocean Lab, this is part of the group. You can visit, as Laura was mentioning this morning, you are welcome to visit our laboratory. It's a 200-meter walk. So, and you will meet all of us during these days. We have a small operational room that you can visit. Today you will see more detail of these two new ocean forecasting systems. Paolo has started to introduce them. But we do also application, and we do application, you will see sea condition, Palmalisa later will present it. You will see tomorrow our activity in search and rescue. Gianandrea will present ship routing. We also are working on new dynamic navigation system to provide products in the proper, also to provide forecast and services in the proper technological mean, like a navigation system. And then this is an example that Paolo has already showed, but we were working with the Coast Guard for the parbuckling of the Costa Concordia. This is those days at our operational room. And this is an oil spill scenario that we were producing in collaboration, of course, with all the partners of TESSA project and also Italian Coast Guard, Met Office, Hydrographic Institute, and ISPRA. Another example of storms, no, it's not really, well, it's sea level forecast. So we are using the ISPRA tide gauge as an observation, and then Antonio Bonaduce with a group of ours researchers has produced this way of forecasting the sea level for the next hours, so that in these points we can provide, and this is a combination of a model plus different type of models and the effect on the sea level, like wind effect, wave effect, all put together in a forecast to predict the sea level. Another challenges, I think, is to disseminate our product and also to do some ocean literacy. So we are trying to start these activities. We have been in a theater to present operational oceanography to people that never have seen it. We are following this project that will sail all along the coast of the Mediterranean and Black Sea, and we are supporting through sea conditions and ship routing system to disseminate our information, and of course we organize conference. So the challenges for the future, of course, is to increase the capability of predicting the system, but also to estimate the accuracy in doing that as much as possible, both for the past and for the forecast, to understand the change and impacts of human activities and describe or develop adaptation strategies, design a cost-effective observing system is very challenging because funding is not extreme, so we have to optimize, and of course continue to develop downscaling. I borrowed this slide from EMODnet. Is the in situ observing system of the Mediterranean Sea as it is today, but then you see easily gaps. for instance. So for mongoose, not really for Shell Lab, it's too big effort, but for mongoose, for our network, this will be a challenge. So we want to populate, or to try to populate with African colleagues and the European Commission the observing system also where it's missing. Going back to my first slide and to conclude, of course we need to continue to develop system for ship safety, but also we need to develop reanalysis, a very high-resolution coastal area. We need to do risk mapping. Tomorrow, Svetlana will present some first attempt. We need to do to develop the concept of ocean literacy also for touristic activity and to develop services in that sense. As Giuseppe Manzella was mentioning, we need coastal observatories, and of course we need reanalysis and future climate change scenario and couple model for climate studies. So this is just an overview of the future challenges. Thank you.
Thank you. Thank you very much, Giovanni, especially for being so short, so that we have a little bit more room for questions. And I think 2 questions are allowed now, if you have any. We have one here, then I have the second, if nobody else.
Yeah. Again, Giovanni, essentially, I want to ask just some details about ocean literacy. Essentially, the main problem is to transform data into information, and Professor Blumberg said to me, but in this case, you have to also to transform the information in knowledge. What kind of activity in this kind of a transformation are you doing in CMCC?
Well, these were just extreme examples because I wanted to show, to provide some ideas also to. So, of course, the way of speaking about the ocean can be different from what we are used to do in conference. So, really, it was an experience to speak about the ocean in a theater to people that ever never. So, organize such events. I think it might help. But another example is this, to connect to, let's say, this is a sailing project, is a cultural project, so to connect to reality that are different from the common scientific understanding. On the other side, there is an effort, and Palmalisa will show later, an effort of distributing the knowledge through new applications. So, for instance, sea conditions, I think, is a way of I mean, the forecast is already available on the website, but to reach the iPhone or any mobile platform is an effort, is a technological challenge, is an innovation, and this could allow to broadly distribute, in this case, ocean forecasting. On the other side, as the crowd sorts, so the information that we can collect through the social network, I think we have to invent ways of involving the people, I mean the community, the normal people, to provide us information. And I mean the best example was shown that they are even providing you observation, not only photo or but really it's something that can be used and they can be. So I think this will be the way of examples on how to interact with the public.
One more question.
Good morning, I am Franco Zaghetti from ENEA. My question is a good invitation to owner of ship working in the Mediterranean to facilitate the activity of installation of sensor on their ship, and the collaboration maybe also in the deployment of sensors such as Argos, glider, and so on, because it is really very hard for people working on the sea to have money, to have a research vessel, and so on. Satellite data can cover a good part of observation, but the in situ measurement are fundamental in order to have a good forecast. So I think that we need a good support at high level in order to have a good collaboration.
I totally agree, Franco. I mean, what we call ship of opportunity, and Franco later will present this capability of installing or using ship, like cargo or ferries, or not to research vessel, to monitor the ocean. It is very important. I think we are doing as Mongoose our effort to further develop it in the Mediterranean. Of course, we have to collaborate with EUMETNet, so with net offices, in order to optimize the strategy so that the same instruments can serve different communities. But we could also offer services to ships, like sea conditions or any search and rescue oil spill services, and exchange this offer I mean, asking them to install or equip the ship with instruments or host personnel on board. On the other side, we could also discuss with EMSA or other agencies in the Mediterranean Sea how to push a bit the ferry and cargo ships in order to welcome on board this type, maybe even just disseminating the information to them, because it's zero cost it might be a very low cost for them, but then they can get benefit for their safety of navigation. So I think it could be a good point for discussion to exploit some projects.
Thank you again, Giovanna.
May I give just an information? Sorry, Giovanni.
Yeah.
Regarding your map, you show us a map with a gap.
Yeah.
So I would like to inform you that in Tunisia, so we have...
I know, it's not a fair map, but it's what at least Europe knows. I know that in Tunisia there are systems, observing systems.
Yes, I would like just to inform you that we have acquired 4 buoys that are so giving the data in real time.
Okay.
2 of them are founded by Japan through the UN program for development, 1 by the EU, and the 4th one will be founded by Italy.
Yeah, I mean, I'm sorry they were not in the map, but they were not in the map not because they don't exist, but because they are not yet connected to Mongoose, and I think this is our challenge. I mean, that's why we invited all African partners here to discuss really how to solve this issue of connecting the observing systems and put them all together, and vice versa, offer to African colleagues all what we have developed up to now.
Thank you. We need to go further. So now I leave the word to Samuel Javidnia. Again, I hope that I pronounced this correctly. He's coming all the way from Portugal to give us, to open the lens from the Mediterranean to the European level. So thank you very much. Samuel, when you're ready, you have 20 minutes.
A very good morning, ladies and gentlemen. Let me introduce myself. My name is Sami Diavidnia. I'm actually Italian, even though the name doesn't sound. So it's a real pleasure for me to be here in Lecce. I'd like to thank Giovanni and Leonora for inviting EMSA to be present at this conference. What I will be doing is I'm going to change a little bit the emphasis of the presentation, because EMSA is not an operational oceanography agency. It is not even a research and development agency. What EMSA is, and EMSA stands for European Maritime Safety Agency, we are one of the regulatory agencies of the European Union. What we do is we provide technical and operational support to member states and the European Commission in everything that has to do with maritime safety and security. We have our own legal identity, which means that we are governed by our administrative board, which is composed by members of the European Union member states together with the Commission. And basically, we are a disaster agency. The reason why we were founded was in response to several disasters that happened at sea. You have there some examples. We have a staff of approximately 240 representing more than 20 different nationalities. And we're divided into 3 departments. My department, or at least the department I work in, is the operations department. And that's where we deal with the monitoring of vessels around the European seas and globally, as you will see. Our headquarters is in beautiful Lisbon, maybe not as nice as Lecce, but I recommend you come and visit. So I'll briefly go through the maritime applications we either co-host or host and manage at EMSA. If I'm talking with too many acronyms, just stop me and I'll slow down and I'll try and explain more what I'm talking about. So probably the biggest application we work with is called SafeSeaNet. And you will see throughout the presentation that our modus operandi is very similar. So there is a European directive, legislation that all member states have to adhere to, and therefore that's where we come in support of the implementation of these directives, and in this case is Directive 2002/59, which talks about maritime safety in general, and in the construction of community vessel traffic monitoring and information system. So what this system does, it collects vessel position data and information about the vessel itself in terms of cargo or the port where it's going. And it's collected by coastal stations, so stations which are very close to the which are on shore. I know it's very exciting, sexy. This system was set up starting in 2004, and it's been operational since 2009. It is managed by the Commission and EMSA on behalf of the Commission and all of the member states, and we have approximately 2,500 users scattered around all of the European Union member states. It has a governance body which is composed of both the member states and the Commission, which meets every 6 months to discuss what is currently available and ways to develop the system further. This was the short range, let's say, view in terms of. Can you still hear me? Yeah. In terms of the long-range system, what EMSA manages currently is the long-range identification and tracking data center. So again, there is a regulation that governs this. This is not at European Union level, but it's at IMO level. Basically, it provides only the vessel position by satellite every 6 hours. So while the first system we were looking at can give you constant information, but once you go away from the coast, you are not able to receive the signal anymore, this system provides you with information every 6 hours all around the world. But it only provides you with the position. It does not give you information on the cargo system. And then what we do is, since 2007, operate the Clean SeaNet system. I guess this is the one you're probably most familiar with. It replies to a specific directive, which is 2005/35, where it was stated that EMSA should support all of the European member states in the implementation of the directive by providing satellite-based information. So what we do is, throughout all European states, we provide possible oil spill detections, and we have approximately 500 users scattered in more than 60 different authorities around Europe. Giovanni asked me to go a little bit more in detail about Clean SeaNet. So what we do is we collect synthetic aperture radar imagery, and these imagery are analyzed and possible oil spill detections. When these possible oil spills are detected, then the information is sent within 30 minutes to the different authorities in the European member states. We currently process approximately more than 2,500 SAR images a year. We buy the licenses from either commercial entities or we gather them from satellites from the European Space Agency. So we were actually very happy a couple of months ago or a month ago when Sentinel-1 was launched. We have a distributed network approach, meaning that we have regional service providers which are scattered around Europe, who they receive the imagery, analyze, and then send us the information. What is very important is the near real-time effectiveness of the service. So between the time of satellite overpass and the alert which is sent either via email or via SMS or from the web page itself, it's on average 30 minutes. And the response is passed to the different response authorities, which might be Coast Guards, Navy. This depends on the member states. So this is to summarize. What we do is we sit together with our member states and ask them for their temporal and coverage requirements. Then we go to the satellite operators and we plan the images accordingly. And when the image is taken, is processed, the alerts and the products are provided to the users thereafter, usually 30 minutes after. All very good. We have what we've seen now is that we have several systems which are, let's say, built on different pillars. They respond to different legislation. And in some cases are specific to one user individual community. But what we have seen analyzing the users that we have was that a large amount of these users between the different applications were actually the same. So what the users were asking us was to put together the data, the information, and the knowledge that was coming from these different applications. If we add to this the political will and drive, both at IMO level and at European Union level, to come up with an integrated maritime policy and different new founding regulations that were included in the EMSA regulation, then we embarked on a project which was to bring together these different types of information in what we call the integrated data maritime environment. We had to look also at the different technologies that were available. As a European Union operational regulatory body, we don't have that privilege as research centers have, let's say, to be ahead of technology. So we basically, what we do is we run after technology all the time. But one of the main aspects of technologies that came up in the market that we were following was availability of satellite AIS. If we go back to SafeSeaNet, which was the service that provided the position reports, let's say at near or close to the coast, the signal which is sent from the ship and picked up from your coastal station can also be picked up by the satellites. Now, while 4 or 5 years ago there were hardly any satellites with such a payload and such an antenna, now the situation has developed considerably. And what we can do now is that we can monitor actually the ship positions at global level with all the information that's within the AIS message, that being where the ship is going, the cargo, at a far less frequency. So depending on the constellation of satellites, we're able to have to go from the 6 hours that the LRIT was giving to almost half an hour. Then, of course, there is the availability of optical imagery. 4 or 5 years ago, there were far less satellites available to give high resolution data, or maybe it was just harder to get hold of this data. So that was another aspect that we were looking at. And of course, the emergence of the mobile platforms. While I can argue that most of our users are traditional users that maybe are sitting behind a desk in an operations center. Of course, the fact of having information delivered to your mobile device, whatever this is becoming more and more important. So that linked with the emergence of standards and interoperability principles, and the fact that we are able right now to digest a large volume of data, is what triggered us to move on in our technological platform. So this is what we try and bring together right now at EMSA. We have the SAR imagery for oil spill pollution, we have the LRIT messages, we have the satellite AIS messages, optical imagery, and other systems, and the VMS is specific for the fisheries community. And by trying to bring all of this together, then we can provide an added value to the different types of end users we have and we're working with. So we currently provide a number of integrated maritime services. The first one is to our traditional, let's say, maritime safety and security and environment community in the member states, with all of this data integrated. I'll probably go rather quickly through these. It has more of a regional perspective, of course. It's not country specific. A lot of our users in our member states have their local traffic position already. This is to complement what they have a regional and a global level. We provide a service to the European Union naval forces, which are based in the Horn of Africa, for anti-piracy support, for merchant fleet monitoring. We provide also a service to the European Fisheries Control Agency, which is based in Vigo, and the fisheries monitoring centers that are part of the network for fisheries control, and this is to identify any illegal fisheries activity that happened during campaigns. So while before they only had information coming from their blue boxes, the VMS that I showed before, right now they're able to have a whole wealth of additional position information data that helps them analyze and identify any illegal activity. And then we have one of the last services is a service to Frontex, which we provide in the context of Eurosur, and we provide maritime surveillance data for them to enhance their picture. Some examples of these services, this I've taken from the Italian Coast Guard. So right now, they have a big gap in this area here, where the coastal stations do not pick up the signals, so they don't know exactly at high frequency what the traffic is right here. So with the emergence of satellite AIS data, then you can see that the traffic picture is greatly enhanced here and here as well. We have, let's see. This is a case of medical evaluation, which was provided to us by our Irish users. There was a case of a vessel with Panama flag that was in medical emergency. However, and they called Ireland, but Ireland could not see this vessel because it was emitting LRIT data, and with a Panamanian flag that unfortunately for IMO rules cannot be seen by Ireland. But through satellite AIS, they were able to pick up their position, and they asked them to change route, and then from Ireland a helicopter was sent to pick up the injured person on board, and then the vessels continued on their journey. This is an example of an oil spill case. What we're seeing more and more right now is that the users are switching from the Clean CNET web user interface to the IMDate because it has more vessel information and they're able to pick out more vessel tracks which might provide information on the possible polluter. Okay, so what metocean data are we currently using in our services? Well, to be honest, not that much. And maybe this is one of the reasons why I'm here today. We have an ongoing collaboration with Puertos del Estado, and they were kind enough to give us access to their buoy data, which is available publicly. But I think the message here was it was very easy to integrate the information from Puertos del Estado in the application. So we have waves, temperature, currents, and winds data from them. This is, maybe you cannot see it very well, they provide us time plots of the different variables, and what you need to do is you click on one of the icons of the buoys, and then it gives information which you can navigate back in time as well. Then one probably of the most important elements is the collaboration we have with the modeling community in and around Europe. So clearly EMSA, as we're not an oceanography specific knowledge agency, we don't have the tools and the knowledge to run the models. So what we do is that we connect to the different models which are existing around the member states. So our end users pick their model of interest, and when an oil spill detection arrives in Clean CNET, this information is sent to the model. The model then is run in hindcast and in forecast, and then it gives back this information to Clean CNET or to EMSA for this to be displayed. We currently have a collaboration with the Royal Belgian Institute of Natural Science, with the Swedish Meteorological and Hydrographic Institute, and with the Instituto Superior Técnico of Lisboa. I know my colleague Anne-Marie Hayes, who's not here today, has been already talking with Giovanni and the team for linking the MEDES products to Clean CNET, and we're very much looking forward to this as well. User requirements, I'll skip, and this is my last slide. So, in terms of user requirements, what we've seen is that the more we develop new integrated services, and the more our end users are asking for net ocean data. This is very clear. The sea state information now, the nowcast and forecast, is very important to support their operations. However, currently, the products that are available within MyOcean are not tailored for these services to be provided. What we need is to have more of a downscale of these products to cover the coastal and make them available at higher resolution. There will be a MyOcean user workshop actually hosted in Lisbon at the end of June. I was lying, this is my last slide. I just want to pick up two messages from here. What we see from the user perspective is that we need to, as much as possible, move from a purely technology-driven approach to have a more user-driven process, so that we are able to understand what the user needs in terms of products. So one of the speakers before said it's all very well if we have these fancy products, but if they're not used at the end of the day, then they're not that meaningful. And one thing we have seen is that we're not looking for the data itself. What we're looking is for to consume standard and interoperable services that gives the information and the knowledge, and these need to have high operational performances. A lot of the time we start collaboration, cooperation with either research institutes or other entities, but they're not able to have the sustainability of the services that is very important. So it's no good to provide a product for 1 week and 2 weeks, and then the 3rd week being off and the 4th week as well. What the users in the maritime community need is to have a highly performant and highly available service the whole time. With this, I close.
Thank you. Thank you very much, Samuel. I am impressed because I'm understanding so much, which means that you're really speaking clearly today. Are there any questions? Is there one question? Because then we have to go to the coffee break.
Thank you very much for the presentation. I see you're challenging us, and I like it very much. And I see at least four items for further collaboration. One, of course, is MEDES for MS. Tomorrow, Stratos will present it, and it's true we have been working with Anne-Marie to link, because that project is funded to develop one service dedicated to EMSA. So, I mean, it should be easygoing, it's a matter of time. The second answer to your question is MyOcean. I was discussing, we were discussing with Pierre Baurel and Dominique Baton from MyOcean. They are dedicated now to serve EMSA for connecting, for providing you in the proper format the ocean forecasting and observation. So I think we should focus on that in the future, because we have a solution there. But you also pose two nice challenges. One is, and I think the Mediterranean could be helping you, one is the downscaling to coastal zone. Because we know the users like Italian Coast Guard and REMPEC are already stressing that they need high-resolution data forecasting in the coastal zone. So I think Mongoose is already coordinated to provide, and we need a project to do that together. So we can do it. Of course, MyOcean is the first step, because we'll provide you a pan-Mediterranean and pan-European forecasting products. But on the other side, if you want to go high resolution in the coastal area, we need to work together in the Mediterranean community. Last but not least is the radar, HF radar service. I think we should join the effort on that. There was a call that they postponed. We wanted to do it for radar for search and rescue. They postponed it. It's a EU call. I know that you cannot participate, but on the other side, I think we can, as we did for MEDES, plan it together. And I mean, join the effort, because radar cost, but they can serve multiple purposes.
Absolutely.
So, like ocean observation, as Professor Bloomberg was showing, but also safety of navigation. So I think it's a very good example for future collaboration.
Yeah, do you want me to reply? Well,
if there is any reply to.
Well, let's say that I'm very happy to hear what Giovanni is saying. I think one element which we have to, let's say, increase our understanding is how we interface, and the fact that up until now, it is true, MyOcean data was available, but sending, and I'm sorry for the audience, NetCDF data, which I agree, it is a common standard for everybody, it's not really the solution, at least for EMSA type users. So if we can speak at technical level, and are able to define these standard interfaces, not to have the data on our side, but to have the knowledge transferred, or the information knowledge transferred on our side, it's a win-win situation. And the HF radar service, well, I'm really happy to hear this. I have been through other channels in contact with NOAA, that you probably know very well, already have such a system serving both coasts. They provided to me some very clear examples of how it can be used for pollution, for navigation, for safety. So I very much look forward to the development of that service.
Okay, thank you, Samuel, again. I think it's now time for a break.
Yeah, I just want to inform you that the coffee is served going toward the exit, just before exiting on the left. If you go on the right, there is a wine convention. You can enjoy more, but then we will probably have some problem in continuing our discussion. So please, go to the left, not to the right.
Yeah. break. So we start again the second session of the morning, and I invite Claudio Polignano from the Regione, from the local government, to give a short address. Thank you very much.
Thank you. Just 1 minute for a very short address and greeting from Puglia region. Let me introduce myself. I'm Claudio Polignano. I come from Puglia region, the regional government of Puglia region, and specifically from the Mediterranean department. The Mediterranean department is the sector of Puglia region in charge for the governance of the entire territorial cooperation programs. So we manage all the programs, the cooperation programs. And mostly in the area of Mediterranean and Adriatic Ionian area. Thank you very much to the CMCC, the Euro-Mediterranean Center for Climate Change, for the invitation in this interesting meeting dedicated to the Ionio project. The Ionio project is, as you know, financed by the Greece-Italy cross-border program in the context of territorial cooperation financed by the Member States and the European Commission. And thanks to this program, we have the opportunity to support a lot of projects in the context of marine strategy, marine affairs, in line with the European strategies. More or less 80 projects, mostly focused on maritime safety, on sea transports, on port security, on marine affairs in general. And also for the next programming period, this program is confirmed. So we have for the next programming period 14-20 a new Greece-Italy program as one of the European most relevant initiative for the safeguard and valorization of the Adriatic-Ionian Sea Basin. But also other programs will work on the same strategy, marine strategy. For example, the Italy-Croatia programs focus on the Adriatic Basin, but also the Adriatic-Ionian initiative, the Adriatic-Ionian program that will involve the Italian coast, the Italian regions on the Adriatic Sea, but also Slovenia, Croatia, Albania, Montenegro, and Greece also. And mostly the new program for the pre-accession, Italy, Albania, Montenegro, whose topics will be focused surely on the Adriatic-Ionian macro strategy. So the most relevant topics of these programs is that they will be based on the Adriatic-Ionian macro-regional strategy, an initiative supported by the European Commission on a strong commitment by the Italian government. All the USAIR strategy, as you probably know, is based on the EC communication marine strategy for Adriatic and Ionian space. USAIR strategy will be based, we are waiting for the action plan in probably next month in June, and all the strategy will be based on 4 pillars. Blue growth, transport and connections, environmental quality, and sustainable tourism. As you probably can understand, the entire strategy will be based on the sea, and so we all have a new opportunity to work on the sea strategies. In particular, the first, blue growth, and the third pillar, environmental quality, are probably the most relevant for the valorization and of the Adriatic Sea, specifically the third one, environment, dedicated to environment. And they will address the challenges to the following topics: marine biodiversity and pollution of the sea. These are the most important topics. Connected to other relevant issues such as integrated coastal zone management, maritime spatial planning, and climate change adaptation. I suppose, and I hope, that this synthetic framework of the new programming period, European programming period, will give you an interesting opportunity to give a follow-up to the Ionio project and to capitalize the results achieved so far. Again, I wish you all a fruitful work for these 2 days and for this conference. Thank you.
Thank you. Thank you very much. It's now time to connect to via web to Greece, because we have now Leonidas Perivoliotis from Greece, who will be speaking about Hellenic forecasting systems. So it should be shown on the screen.
Stiamo facendo la parte per aspettare 5 minuti. Grazie a te.
Yes.
Go ahead. You can start.
Okay. Hello to everybody, even through web. I would like to first apologize that due to some personal constraints, I'm not able to be with you in this Ionio-sponsored conference. And I'm going to present our forecasting systems that have been developed the last years, the last 10, 15 years in HCMR. As you know, this is more or less the work that has been developed and applied and implemented by Dr. Gerasimos Makis. So he will not be able to attend the meeting either, because he is now in a meeting, in a MyWave meeting in Crete. So I'm going to present our activities on his behalf. And by starting, I have in this beginning slide, you can see that this is accumulated work has been developed through several projects, national and European, that has been developed and applied to our current state of forecasting system in the Hellenic Center of Marine Research. So the main three pillars of the ocean forecasting is to have a multidisciplinary, multi-platform observing system with permanent and reallocatable, it should be. A suite of numerical models providing forecast for hydrodynamics, wave, and ecosystem, which should be coupled synchronously or asynchronously to atmospheric forecast. And of course, we need also a data simulation scheme that produces analysis and combining observation and model forecast. And of course, additionally, the operational oceanography and ocean forecasting involves, as you know, techniques and tools from downscale, from large scale to regional and local scale, tools to nest smaller domains to larger domains, continuous production of forecast of relevant environmental variables, and various services utilizing the ocean forecasting projects. So this is the current an overview of the current infrastructure that has been already operated in our forecasting system in HCMR, the Poseidon forecasting system. Poseidon is the Greek version of the operational oceanography activities. So this is our forecasting system. It is the hydrodynamics that is connected to atmospheric model, which is our atmospheric model is built on the ETA model. It's a regional model. We have also introduced in this atmospheric model a system of applying a sophisticated analysis in order to produce analysis fields. We are now providing 5 days forecast. The blue arrows show the current and active situation. The red, it is our current research and forecast, and the yellow indicates what we are going to do in the future. So we are also have already implemented a data simulation scheme to hydrodynamic forecast based on LSIC. And we also connected in our system the wind waves. We have already a component for forecasting the wind waves, which is realized by implementing both WAM and wave forecast model. And as you see, we are now currently trying to have a coupling between the wave forecasting and the hydrodynamic forecasting, and trying also to have another coupling between the wave forecasting and the atmospheric forecasting. And of course, trying to implement, exploring how we're going to do also a data simulation scheme in the waves. And of course, we have an ecosystem functioning forecasting system that now is connecting to one way to the hydrodynamic model. And now we are trying to do some data simulation scheme focused only for the ecosystem model. And in the future, the yellow arrows indicate that our vision is to have a total coupled system with all these models. And finally, from all this suite of models, we are producing services that are available to our website. So to see what is exactly now is already available in Hellenic System for Marine Research, there is the atmospheric model, which is covering the whole Europe and the Mediterranean, providing weather forecast in an analysis of 1/120th degree. It is based, as we see, in a regional model. It is the analysis about 5 kilometers, the spatial analysis, and it produces forecasts for the next 5 days, 120 hours. It is gained and it receives boundary conditions from the NCEP model, downloaded every day from NCEP facilities. This is the domain, how it is produced, and the snapshot of our forecast. Then we have the hydrodynamic forecasting. We have operational forecasting for Mediterranean Sea in 1/10 degrees analysis, in Aegean and Ionian, thanks to Ionio project. And we have also on demand the ability to produce the forecasting in a coastal area with spatial resolution higher than, lower than 1 kilometer. So this is our implementation of hydrodynamic model in the Mediterranean. It is 1/10 degrees. We are forcing our model with our forecasting, our atmospheric model. This is a snapshot of the salinity. Then we have nesting in this Mediterranean model, Aegean model with analysis of one of 30 degrees. And also forcing this model with our ETA forecasting system, Poseidon forecasting system. And this is the version of what we have already produced through the Ionio project. It's a spatial resolution of 1.1 kilometer. It's a very high resolution analysis, and it is nested in the Maiorthean, the MFS, the Marine Corps Service product that is produced on daily basis by INGV. So this is more or less what are currently doing in HGMR. We have a basin scale model, downscaling to Aegean, and then we can go even further to coastal hydrodynamic applications, providing data. This coastal hydrodynamic application is currently under demand and is not in daily operational cycle. And then we have the wave forecasting system, providing 5 days forecast in daily basis. It is forced by our forecasting, atmospheric forecasting system. We have implemented 2 different waves models. The one is WAM, which is based on cycle 4.5, and we have nested in this scheme 2 wave forecasting in much more detailed analysis, one for the Aegean and the other for the Ionian, which is required by Ionio project. And this is also another implementation. We have one implementation both for Mediterranean and Black Sea in 120 degrees analysis, both for Mediterranean and Black Sea, and this is a WaveWatch 3 implementation. So this is some snapshots about the efficiency we have noted so far in sea surface elevation that is now produced by our model. We have implemented a different and separate module for sea surface elevation forecasting, taking into account also the atmospheric variation. And this is our forecast for 2 Venice floods, one in 2008 and the other in 2012, which is close to what actually happened and observed in Venice. And this is one of our, let's say, forecast skill regarding the wave. This is an incident happened close to Marseille, where a huge wave kills 2 people on cruise in Mediterranean in 2010, and this is how this area that is forecast by our WaveWatch model for this specific day, 48 hours before, indicating significant wave height that is over 7 meters. Furthermore to that, we have also services, Poseidon services. That the first one, it is interactive. It is oil spill forecasting that is available for the Ionian and Aegean seas, not for the whole Mediterranean. It is based, it is an oil spill model that is based on Poseidon oil spill model. The products of this model is the dispersion of the oil spill, evaporation, emulsification, beaching, and sedimentation. And we have built for this oil spill forecasting a web service, so the user can submit a simulation scenario through our web page, pointing and selecting the initial location of the incident, the date and the time, the duration of the simulation, the oil spill volume that it is passed in the sea if it is known, and how much is the evacuation time, meaning if it is an instantaneous dispersion in the sea or not. So after a while, the user is noticed through email to visit the website and see the result, which is accessible through our web. Also, we have now given the facility of downloading the results in file and also in KML format for much more fancy presentation of the results. We have also developed a search and rescue model, which is working using our forecasting of weather and currents. And this is not, it is based on Leeway model. This is not accessible through a web, but it is connected and it is used since 2012 through, it is used by the Greek National Search and Rescue System, which is operated by the Greek Air Force. So it is part now of a national search and rescue system which is used daily in the Greek seas. All this information, it is available through our website, which is experienced more than 1 million user sessions per month, but most of them are interested about the weather forecast. But all this information is combined information from all our forecasting products, and all the data that are collected from our Poseidon system is available through this website. So, yes?
Can you hear me?
Yes?
Say that you have still 1 minute to go, please.
Yeah, I'm finishing. Yeah, I'm finishing. So our current research and development, it is in wave current direction and ways how to introduce them in general circulation model. This is developed through my Ocean 2, nesting the Mediterranean Sea model with a modeling system of Marmara and Black Sea, which is also developed through my Ocean. Atmospheric and wave coupling, which is developed through my Wave project. A data simulation system for high-resolution hydrodynamic model, which is funded by our national project system. And of course, we have developed an observation system simulation experiment, which has been developed through Jericho FP7 project. So the final slide is our priorities and target for the next 7 years. To have modeling system upgrade, where we are intending to implement a new hydrodynamic model, probably ROMS, to run in parallel with POM, improve horizontal analysis, open boundary conditions, and introduce a wave current interaction terms. Extending our operational oceanography to the coast, which is now the coastal oceanography component that will now tend to much more better introduced in the next years, and introducing, let's say, in key areas such as Saronikos Gulf. And of course, to improve the wave forecasting, introducing data simulation scheme in basin scale with close collaboration with the European wave community. And in the long term, to have coupled system, all these models, coupled atmosphere, wave, and ocean prediction system to be produced in a one-way coupled system. So that's me. Thank you very much.
Thank you. Leonidas, thanks a lot. I think we need now to go one step further. So thank you again, Leonidas, and I'd like to introduce now Stefania Ciliberti from the CMCC. Again, remember you have 12 minutes to speak and 3 minutes for questions.
Good morning to everybody, and my name is Stefania Ciliberti, and I'm in charge on the development of the Adriatic-Ionian forecasting system. I would like to thank my colleagues at Ocean Lab, and especially Paolo and Giovanni. Here I present our models, regional models at high resolution for the Adriatic-Ionian basin, starting from the models that are available and operationally already available at the Ocean Lab in the framework of Ionio and Tessa projects. Then I'll discuss about the Adriatic-Ionian forecasting system, and in particular how the model has been defined, the numerical implementation, and the first results. Just a brief introduction to the main projects that allow us to develop this research. The first one is the Ionio project, which would define a monitoring and forecasting system at high resolution for the Southern Adriatic, Northern Ionian area. And the second project, Tessa, which will provide both products and services based on, of course, on high-resolution model for the situational sea awareness, the development of advanced decision support system based on a robust technological platform that will be described by my colleagues in the next presentation. The key words that are important both for the Ionio and Tessa projects is the high-resolution model. So, in order to achieve this, to reach this goal, we adopt a nesting approach. So starting from a general circulation model available for all the Mediterranean Sea, we started to develop the Adriatic forecasting system that covers all the Adriatic Sea, and it is our first product currently operational, plus an extended version of the Adriatic forecasting system that include also the Ionian Basin, and the core model is called IREG V1, Adriatic-Ionian Regional Model, which had been updated in order to include also the Tyrrhenian Basin that plays a role into the general circulation pattern that is developed through the Ionian Sea and consequently also to the Adriatic Sea. So this system will be converted as a forecasting, this model will be converted as forecasting system. And in order to fix some issues that guide us to develop these new numerical models, of course, the spatial resolution and the treatment of the physics, in particular the surface boundary conditions and the lateral open boundary conditions, are able to make the Adriatic-Ionian forecasting system a high-resolution model for the central Mediterranean area, starting from the theory based on the Mediterranean forecasting system and the consolidate information available for the Adriatic forecasting system. So, as I said before, the Adriatic forecasting system is our first operational product. It was developed by the Italian Group of Operational Oceanography in 2003 and currently is maintained operational by Ocean Lab. It is based on Princeton Ocean Model, and comes with a spatial resolution of 2 kilometers with 31 sigma levels along the vertical direction. with the daily frequency, the Adriatic forecasting system produces temperature, salinity, currents, air sea fluxes, sea surface elevation, and wind stress, and all this information are available at our web page. I skipped the general setup of the model that is define the daily forecast cycle of the Adriatic forecasting system. And here I'll present just a screenshot about a typical output that is available at our website. It is possible to find all the products previously listed, plus some specific zoom on sub-regional areas such as the Southern Adriatic Sea, but also the Taranto Gulf, the Trieste Gulfs, and so on. Another activity, research activities is developed at the Ocean Lab, and it is related to the Adriatic forecasting system validation. Daily, we produce maps for AFS model simulation and forecast and satellite sea surface temperature comparison in order to check the reliability of the model to provide high quality information and about the state of the sea. And there is possible also to visualize some statistical variables, and by using a web user interface, all the information for the AFS are available at the web page. Then the second system that is ongoing development is the Adriatic-Ionian regional model. As I said before, there are two systems. The V1 version is still maintained in order to investigate some specific physics of the Adriatic-Ionian basin, and the IREC V2 model that includes also the Tyrrhenian Sea, and which is the focus of the presentation. Regarding the V1 system, a sensitivity study on river influence has been provided in order to understand the influence of the river in freshwater and to perform our forecast with respect to specific features of the coastal zone, such as the rivers contributes. And regarding the IREC V2 system, one of the major improvements is related to the treatment of the lateral open boundary conditions by using the flow relaxation scheme for tracers and velocity, plus a flatter condition for the barotropical velocity normal component. In addition, in order to preserve the conservation of the transport across the inflow-outflow sections, an interpolation constraint has been applied in order to correct the final velocity field that will be passed as lateral forcing to the Adriatic-Ionian regional model. Another aspect that is very important to be highlighted is the IFS spatial discretization. As I said before, the model comes with a resolution of 1:45, and it uses 121 zeta levels that ensure a vertical thickness of 0.8 meter at the top, and the upper layer is completely described by 42 vertical levels, while MFS, that is our model, the father model that is used in order to nest AFS, comes with a vertical thickness of 1.5 meter at the top, and the first 150 meters are covered by 22 vertical levels. Okay, very quickly here I summarize the main features regarding the surface boundary conditions, in particular the bulk formula for computing fluxes by using the atmospheric forcing provided with the daily frequency by SEMWF, plus an update about the river runoff contributes provided as monthly climatological data except the river, the Po River, which is based on daily observation provided by ARPA Emilia-Romagna at the cross-section of Ponte Lago Scuro. The initial conditions come from MFS products in terms of temperature and salinity, while the first run of the model starts considering rest conditions. About the lateral open boundary condition, a tool has been developed at the Ocean Lab in order to provide correctly the lateral information in terms of temperature, salinity, UV, and sea level to the model. It consists on the modules that perform the interpolation of the MFS data to the IREG grid, plus a nesting module that includes also the interpolation constraint, and a reshaped data structure in order to provide the information according to the BDY module that is provided by the NIMO code for imposing the lateral open boundary conditions. And finally, regarding physics and dynamics, horizontal viscosity and diffusion are traded by using a Laplacian operator with coefficients that have been scaled opportunely according to the horizontal spatial resolution of IAFS, while regarding the vertical mixing, the Pakanowski and Philander scheme has been applied. The scheme which used for performing the time integration is the split explicit free surface with a time step equal to 150 seconds. Here I present some results provided by the annual run in terms of daily mean fields at the last day of the simulation. I simulated all the 2013 so starting from the 1st of January until the 31st of December, and typically we work with maps daily mean in terms of temperature, salinity, sea level, and currents, and all this information, of course, should be validated by using observed data. I skip and another activities related to the diagnostic analysis in order to compute some specific features in terms of time series of the mean volume for temperature, salinity, mean surface elevation, and the kinetic energy. Okay, the improvement provided by AIFS can be observed also for describing the general circulation pattern at in the Adriatic Ionian Basin. I skip this part that concern a description of the main streams that characterize the whole basin. And here I provide some zoom on the Apulia regions in terms of daily temperature and salinity in order to check the quality of the river inflow, and so the high quality information provided by the model. In the bottom panel, the sea surface 8, and the final figure related to the currents, where we can see how the model well described the central and southern gyres, allowing also to simulate, to capture a specific local phenomena in front of the Gulf of Taran in this cyclone that is highlighted. And finally, an ongoing development is related to the implementation of the tidal harmonic forcing that represent our next improvement. And our next milestones, of course, we would convert in as operational the Adriatic Ionian forecasting system by designing and defining the assessment of the operational chain, finalizing the IFS version with the tidal forcing, and improving the surface boundary condition by using high-resolution atmospheric forcing provided by the COSMO-ME operational data. That's all. Thank you.
Thank you. Thank you, Stefania. If nobody has a question, I do have one. I have a short question. you might find it quite trivial, but as a very end user, I mean, I love sailing and windsurfing, so my question is normally like, should I go or should I not go outside because of wave or wind? Now, when I see these maps, I see these red colors, the scale red to blue, yellow, green, which to me, which I'm not a scientist, normally I read it simply in terms of red, I don't go. Yellow, depends if my kids are on the seaside watching to me, then I don't go. If they're at home, then I go. And green and blue, it's like safe. Should I read these maps this way, or would be this misleading?
Of course, our models provide some high-resolution information that can be integrated on according to the nesting approach that I said before, can be used in order to improve also sub-regional models, like we'll explain even, for example, in the next presentation. But also this information should be used in order to be integrated also into decision support system, in order to provide to the end user a synthetic information to how is the general conditions of the state of the sea, what is the effective situational sea awareness. So all the features regarding the way that the end user can use this information can be integrated on an interdisciplinary platform, as we are trying to develop both in Ionio and also especially in TESSA project. So these are the specific tools that can be and should be integrated on more specific models in order to provide.
But this is not an end user product. I shouldn't just watch it red, I don't go, green, I do. Okay. Thank you. Thank you very much. Next is Ivan Federico from CMCC again. I strongly recommend you please to be short, Ivan, and to all the others to be short, because so we have more time for more room for questions. So shrink, cut, skip, so that we can do more questions. Thank you.
Okay, dear all, I'm going now to introduce the SANIFS model. SANIFS is the acronym of Southern Adriatic Northern Ionian Forecasting System, Coastal Forecasting System. It's a coastal ocean forecasting system dedicated to the Puglia region and also Basilicata and Calabria. But in the context of Ionio, it's mainly focused in Taranto Gulf. Is mainly focused in Taranto Gulf. Just the outline. After a first introduction about the scope of working area, the framework, the aims, we will introduce the methodology. Our methodology is based starting from the oceanographic scale on downscaling and unstructured grid model based on SHIFM code. We will explain a little bit the code, the model, and the validation stages. After this, we will introduce the forecasting system. For what concerns the ambit area of the working area, we can summarize the scope of working area with the three keywords. The first refer to SANI area. SANI is a Southern Adriatic Northern Ionian area, is here highlighted, and however before told, in the Ionio project we are mainly addressed to Taranto Gulf. The second keyword is represented by the unstructured grid finite element model. Here you can see the grid that covers the SANI area, and in the black part, the black part of grid, you have the high resolution that give more information in the coastal area. And the third point refer to the operational forecast, the third keywords. We are going to give operational products in terms of coastal short-term forecast. Here you have a map of forecast related to 31 May. Yeah, I will explain better in the next slides. Okay, just a point, the consolidated models based on a regular, on finite difference model here are replaced with the abstract grid high resolution model that that is going to be a common tool in base research, in fundamental research, but it represents a good challenge for the applied and operational research. But we have a lot of successful implementation in Mediterranean area, for example, with the Cassandra storm surge forecasting system developed by CNR ISMAR. And this can be a powerful tool for the future modeling. Just to how to integrate the coastal model, how the coastal model can support the development or the integration of decision support system. The high resolution coastal model data can represent an input for different DSSs, for different decision support systems. In particular, for what concerns the integrated coastal zone management, can be a useful planning tool for policymakers for what concerns the ambit of coastal protection, coastal erosion. Also, the high resolution coastal model can represent an important input data for DSS of oil spill, search and rescue, and ship routing close to the coastal area. The methodology, how to reach the coastal scale starting from the oceanographic scale. Our approach is based essentially in two steps. The first is the downscaling. The second is to adopt proper modeling components that are represented by the unstructured grid model. How to explain the downscaling, starting from the Mediterranean forecasting system that represent our mother model and is operational. Mediterranean forecasting system provides the boundary condition to the Adriatic-Ionian forecasting system that Stefania introduced in the previous talk. And the Adriatic-Ionian forecasting system provides the boundary condition to the Southern Adriatic, Northern Ionian forecasting system that is the CNFS model that is the focus of this presentation. This represents our nesting cascade approach based on downscaling. In this stage, we are the CNFS model is directly linked to Mediterranean forecasting system. For the future, we will perform this double nesting cascade approach. The second point that we highlight after downscaling is how to reach the coastal area with the proper model. Proper model are represented by the unstructured grid finite element model. In our case, we adopt the Scheife model, shallow hydrodynamic finite element model, developed by Georgum Gisser group of CNR ISMAR in Venice. The model give us the hydrodynamics, is a 3D model, give us the hydrodynamics and tracer field. Just to explain the features of our model, we have a resolution that is in the coastal area, more or less 200-500 meters, and in open sea we have a good resolution in the scale of mesoscale that is more or less 3 kilometers. The model is characterized by 91 Z level. First, the model is is forced at the boundary condition through the MFS field in terms of salinity, temperature, elevation, and currents. And the model in terms of process includes the ties that has been imposed at the lateral boundary condition through the OTPS software that is a tidal prediction model developed by Oregon State University. In terms of surface boundary condition, the model is forced at the surface through the MFS field via MFS bulk formula that give us the surface fluxes. Just to highlight the application field, here you have a plot of the currents with the MFS on your left panel, and on your right panel the SunnyFS plots. You can see that thanks to the high resolution in the coastal area, you have different field that has been bring by SunnyFS, different to the MFS model that is not able to detect some coastal information. You have, for example, this cyclonic gyre, you have the coastal circulation. Also, you can better model the influence of rivers. Here you have the Crati rivers in Calabria. In this larger view, you can see the two different cases. The first refers to Mar Grande of Taranto that represents an area, an industrial area. And here the SunnyFS model can be a good support for decision support system that are related to the emergency state as pollution, oil spill, pollution dispersion. And in the second case, you have a touristic area that is represented by Gallipoli in Ionian part of Salento, and here you can give to the policymakers information in order to protect the coastal area, and you can give also information to the tourists in order to know how will be the circulation in this area, in this coastal area. The procedure has been, the model has been validated in two different stages. The first referred to the validation of SunnyFS fields has been compared with the MFS field in open ocean. Here you have different comparison in terms of temperature, in terms of currents, and also in terms of monthly mean surface temperature. You have map and section of comparison. And in the second stage, the model has been validated with observing data. You have a comparison with SST, surface satellite temperature, and Argo float for what concerns vertical profile of temperature and salinity. Also, you have the time series comparison between the simulated surface 8 and the observed 8 at the Italian tide gauge station. At the end, I will introduce a forecasting for the next Saturday. If you will remain in Salento, you can have here some specific fields for different area, coastal area. For example, in Gallipoli, you have this circulation, and here you have also the temperature. I suggest you to have a good swim here in the area of Rivabella, not in Punta della Suina, that is colder than Rivabella. And then you have other different coastal areas, touristic places as Santa Maria di Leuca and Otranto. The other zoom referred to the coastal circulation in the area of Mar Grande and in the area of Sibari in Calabria. Just to conclude, we introduced the Southern Adriatic and Northern Ionian forecasting system. That is a forecasting system that now is in a pre-operational stage, is under testing. The model is based on high resolution and abstract grid finite element. Will provide us short-term forecasting and can be a useful tool for development and also for integration of different DSS related to integrated coastal zone management, DSS related to oil spills, search and rescue, and the ship routing that you will have different presentation in next talks. Okay, thanks.
Thank you, Ivan. Thank you. Awesome, we stayed in the time, so we have time for one question or a comment.
So you show us that your model presents a small structure compared to MFS.
Yeah.
But how do you validate this?
In the coastal area.
Yeah.
In the coastal area, we have a lot of lack in terms of validation. For example, the first stage of validation has been performed with a tide gauge located in the coastal area. We have 6 tide gauge that are furnished by ISPRA. But the validation in the coastal area different to the consolidated model that have as strength the very many fields, many observed data. In the coastal area, we have a lack of data in order to make the validation in coastal area harder. Yeah.
Thank you again. So I invite now Palmalisa Marra from Links, coming from a professional perspective, from company and private perspective. So we move from the academy to the companies and commercial. Again, Palmalisa, thank you for staying in the 12 minutes and 3/4 questions.
Good morning. I am Palmalisa Marra and I work for Links Management and Technology. Links is a company, a consultancy IT company based here in Lecce. And we are computer engineers, so we are not oceanographer. And we faced for the first time operational oceanography 2 years later with a thanks to a research project. Thanks to the Ionio project, today I can talk to you about sea conditions, which is an example of a downstream service as defined by the butterfly scheme of Copernicus system. Just a few words about the research project within which sea conditions has been developed. The project is TESSA, which stands for Development of Technologies for the Situational Sea Awareness. TESSA is an industrial research project funded by the Italian Ministry for Education and Research under the National Operative Plan 2007-2013. The project aim is to strengthen and consolidate operational oceanography in Italy and particularly in the southern seas by integrating state-of-the-art models, forecast models, with advanced technology platforms in order to improve the way in which we disseminate information about the situational sea awareness. TESSA is an initiative of a group of researchers in operational oceanography field and experts in scientific computing and information systems. So the project partnership is composed by Links, which is the industrial part of the project, and the 2 research centers, the CMCC and the Institute for Marine and Coastal Environment of the CNR. Scientific responsible is Professor Nadia Pinardi. So, Sea Conditions is a service providing oceanographic, sea state, and weather forecast for the entire Mediterranean Sea. It is a unique point of access to the forecast and is based on state-of-the-art wave modeling, advanced oceanographic models, and state-of-the-art meteorological models. Which are data we can provide by means of sea conditions. They are divided into two categories, the oceanographic and sea state. So we have the sea surface temperature, surface currents, significant wave height and direction, wave period and direction. From the meteorological side, we have air temperature at 2 meters, winds at 10 meters, cloud cover, precipitation, and mean sea level pressure. Those forecasts are produced starting from the MFS model for oceanographic and wave forecast, and it has been made available from the Italian Institute of Geophysics and Volcanology, which is based in Bologna. And weather forecast is produced and certified by the Italian Meteorological Service. From the resolution point of view, we have 5 days of forecasts which are updated on a daily basis with time steps of 3 hours for the first 2.5 days and 6 hours for the second 2 days. From the spatial resolution point of view, sea state is derived from the wave watch tree model, and we have the wave direction interpolated at 2 kilometers, and wave period and height interpolated at 150 meters. Oceanographic variables, which are sea temperature and surface currents, comes from the MFS model and are interpolated at 150 meters. Weather comes from the ECMWF model, where we have wind interpolated at 2 kilometers, and the other variables are provided at a resolution of 25 kilometers. When we started to design sea conditions, we aimed at conceiving an easy-to-use service with a good level of usability, also for people who are not expert in operational oceanography or are not researchers. We also aimed at producing a service and to join users where they are. So the service is available both on web, and you can find it at sea-conditions.com, but also on mobile devices. So it has been developed as native app, both for Apple and for Android devices. So you can download it for free by searching sea conditions on Google Play and on the Apple Store. Now I'm going to talk to you about the main features of sea conditions by showing them on the web interface. But I point out that you can find the same features also in mobile version. As you can see here, this is the home page. The focus is on the map here. And on the right side, we have a simple menu by which we can change the forecast we want and the forecast date and time. The forecast is represented on Google Maps, and we use the color to show the data intensity and the arrows for the direction. These are examples about, for example, significant wave height and direction. Here, another example of currents. In this case, we use streamlines instead of arrows to represent the circulation. This is the cloud cover. Just a few examples of data we can provide. By changing the time step, we can see how the forecast change over time. As we use Google Maps, we have interactive maps. So we have the possibility to move the map by dragging and to zoom in and zoom out. getting more and more details about the specific variables we are watching. Another important feature is the possibility to see the forecast trend for a specific point on the map. In this example, we are displaying a significant wave height and direction. Sorry. If we point and click, for example, on Otranto, we can see the forecast trend over the 5 days. Last feature is user preferences. User can set up a set of parameters in order to better display the forecast. For example, he will be able to change the unit of measurement for currents and winds, for example, choosing between knots or meters per second or kilometers per hour. Or to change the way in which the map is displayed, for example, in full screen mode or not, or by showing or hiding the explanatory legend. So, by synthesizing sea conditions is a way to provide map layers. This is the reference architecture by means the maps are produced and provided to the end user applications. On the left, the starting point, which is represented by the data centers, based the one at the CMCC in Lecce and the other at the CNR in Naples. Here, the data centers are in charge to collect and to produce the forecast, which is transferred to the SSA platform, which is hosted by links. And here, the forecast is transformed into maps that are then made available by a map service to the end user applications. The maps are made available by means of standards protocol like the TMS and the WNTS. This way we promote the cooperation application. So we are able to provide the maps not only to sea conditions we developed, but also to other third-party systems like GIS or DSS of ship routing, for example. Sea conditions is the result of a strong interaction with representatives of the final users in order to collect feedback useful for improving our service. But we also have experimented sea conditions in real scenarios like last Coppa Magna Grecia race in 2013. Here I synthesized the users' impressions. Generally, users appreciate sea conditions because it is a unique point of access to weather marine forecast and because it is easy to use and almost reliable. So we know we have to work to that objective almost because we know we have to improve the spatial and temporal resolution as users ask for example, hourly forecast and a resolution of at least 2 kilometers. They also ask for new data. For example, divers ask us to integrate vertical profiles or water transparency. So, starting from that feedback, we are working on a new version of sea conditions in which we will improve the spatial resolution by integrating the 2 sub-regional models, Adriatic Sea for the Adriatic Sea and for the Tyrrhenian Sea and the Sicily Strait. We are also working on My Sea Conditions, which is a customized version of sea conditions dedicated to registered and profiled users. Users will be able to, for example, to save their favorite places and to receive specific information about the forecast for that specific places. For example, bulletin, automatically produced by the system and sent to the users every day. So this last version will be available on July, but we are also working on other improvements like improving resolution for the weather forecast and integrating new data like the bathymetry that will be made available by the Italian Navy, visibility and chlorophyll. Thank you.
Thank you, Palmalisa. If you haven't downloaded the application yet, do it because it's amazing. It's beautiful, easy, and it's really clear to navigate through.
Thank you.
There is a question for you.
Hi there. I'm really impressed, and I applaud this initiative. I have. I don't know, is this available for the general public, for everybody?
Yeah, it's available for free. Yeah.
Okay. And what about, you mentioned your standard system-to-system interfaces,
Yeah.
and those are available as well to everybody?
Yes, we are experimenting this kind of interoperability with other systems like GIS, for example. We are able to provide our layers, for example, for a map server.
Thank you. Now I invite Georg Ungisser, correct gesagt? From the CNR ISMA. He's going to speak about Cassandra Storm Surge Forecasting System. I mean, just the title is it's appealing. I can use it for a news tomorrow. So I'm really curious to hear what you're going to tell us.
Good afternoon. I would like to show you the Cassandra forecasting system. This is a collaboration between ISMAR, Institute of Marine Sciences in Venice, the Institute of Atmosphere and Climate Research in Bologna, and IAMC in Oristano, and also University of Darmstadt. I show you the motivation why we started this kind of forecasting system. You can see Venice. We have the problem of having flooding in Venice every while, quite often, maybe 10 to 15 times a year. And the fact is we are doing operational forecasts for the flooding, for the storm surge in Venice. In order to have an operational forecast in Venice, you have to basically do an operational forecast in the Adriatic Sea. And if you have to do an operational forecast in the Adriatic Sea, you need also the Mediterranean. And so we decided we would basically go directly for a Mediterranean forecasting system for storm surges. And as you can see in Venice, especially at the San Mark Square, we have a pavement which is lower than 90 centimeters, and so that gets flooded very, very often. But however, I have to show you how the Cassandra is, what are the components of Cassandra. It's the hydrodynamic model, SHIFEM, that already has been shown by Ivan. Meteorological model, which is the BOLAM and the MOLOG model in Bologna, and a spectral wave model done in the University of Darmstadt. I also have to show you why we called it Cassandra, just a short historic introduction. Cassandra was the daughter of King Priamo, and Apollo fell in love with Cassandra, so he gave her the possibility of prophecy. And then Cassandra, unfortunately, did not fall in love with Apollo. She refused him, and so he could not take back the prophecy. But he said, okay, you will still have a faculty of prophecy, but nobody will ever believe you. And this is our problem with the Cassandra forecasting system also. Now, meteorological model chain. We have the BOLAM system. You can see this is covering the whole Mediterranean Sea and also the Black Sea. And inside the BOLAM system, there is also the MOLOG system integrated. And you can see the MOLOG system is a very high resolution model with 1.5 kilometers. and 50 atmospheric levels. Inside this, we use the Scheifer model, where we can use basically different resolution in the coastal zone, also in the Venice Lagoon in this case here. And well, we can skip this kind of equations. The only thing I would like to point out is that we also have the potential tide, the equilibrium tide inside the model, and there is also a term which is the loading tide, which I will show you some results afterwards. So we also have the finite element wave model, which is the WWM2, developed in University of Darmstadt, which is a spectral, which solves the spectral action balance equation. And this is our model domain, and what you can also see is the very high resolution inside the Mediterranean, which is, well, 15 kilometers, but then if you go to the coastal areas, it's 2 to 5 kilometers, and close to Italy, it's around 1 kilometer, very high resolution. We also have the Black Sea, which is basically an independent model, which we connected together to the model forecasting chain. So we were doing calibration and verification. We used this kind of data. You see ACMWF forcing. We used tide gauge data and also gauge data in Gibraltar. And everything is published in Ferrarin et al. In Ocean Modeling, if you are interested. So one interesting thing is, if you're working with tides, there is some things that you always get told if you're taking oceanography lessons. One thing is that tides are two-dimensional. There's two-dimensional model is enough in order to model tides. Well, you see, this is results. Just let's look at this, which is basically the sum of all of this. If we do it two-dimensionally, we get this kind of error, which is a little bit over 2 centimeters. If we pass to 3 dimensions, we get an improvement. Why is that? Simply because in 3 dimensions, it's the friction term is better described as in 2 dimensions. If we then use the loading terms, we get even better results. And the last step, this one is, if we use all of this we told you before, and also use the surge on top of the tide, then we get best results. What does that mean if you use the surge? This means that there is also a coupling between tide and surge inside the model, the nonlinear interaction, tidal current interaction. And this can become important. So you see results are very, very encouraging in this case. They basically are a very high correlation in this case. Waves are also very good resolved. I show you some statistics now. The only thing is residual differences of the water levels. What you can see is, for example, in the southern part, in the Ionian part, you can see we have quite a bit of bias in the models, and this is simply due to the fact that we do not resolve for the sea level anomaly, because we have still a barotrophic model, and we would have to have a baroclinic model in order to do this. And if, well, you can see some of the biases. You can see sometimes we have quite high, in the southern part we have quite high errors, but it is a bias, and we should be able to correct this. Anyway, if you look, for example, at the calibration of water level, this is total water level. What you can see is the red points are the forecasts in first day, second day, third day, fourth day of the waves, which are very stable. So it does not really, the forecast from one day to another does not really change results. With the water level, it's a little bit different. First day is the best correlation of 92, 93, and then if you go along with the forecast, the results get a little bit worse. You can see the last one has only a correlation of about 0.8. Well, this is just some examples of the forecasting maps in the Mediterranean Sea. See down here waves or surface currents, for example. The same thing also for the Black Sea. We do exactly the same thing for the Black Sea. You can see very nicely resolved is the coastal current due to winds and also due to the outflowing Danube that is driving these currents. And if you go into our webpage, you can also see the forecasting time series in this case, and most importantly, clearly here, Venice. Conclusions, we still want to integrate some of the new techniques like assimilation techniques, neural networks, for example. As I told you before, we have to use sea level anomalies in order to correct our results for the total water level. One of the most interesting things from the scientific point of view is to connect both models, the Mediterranean model and the Black Sea model, in order to get the dynamics of the Turkish Strait system, right? And well, what I would like to say at last is the future of Cassandra. Well, you know, Cassandra, the fact is that Cassandra was never believed is one thing, but the other thing is that Cassandra really was always right when she did a prophecy. So we also hope that we can be very close to this with our Cassandra forecasting system. Thank you very much.
Thank you, Georg. And yes, we have time for one question at least.
Thank you.
Georg, my question is about your spatial resolution in the model and spatial resolution of meteo forecast.
Yes.
Essentially, so the ECMWF is very coarse.
We use the ECMWF only for the calibration and validation of the system. We use in the operational chain, we use Polam, which is around 5 kilometers in the whole Mediterranean and 1.5 around the Italian coast.
Thanks.
Sorry, if this was not clear.
Thank you. Any more questions? Some more voices, because it's kind of polarized. The questions are coming mostly from here, some from there. I'd like to hear some other comments or remarks or questions from the public. Is there anybody who wants to know more at this stage? Not now. So thank you very much, Georg. Okay, I think I'd like to invite now Dr. Ciccolella. Is it from the Torre Guerceto Marine Protect Area? It's interesting, this prophecy, Cassandra prophecy. Just beware, because I think the public, when you speak about science and then you speak about prophecies, then they kind of have some funny ideas about what you can actually provide in terms of forecast. Or what do you think? Okay, thank you very much, Ciccolella. You have 12 minutes speech and 3 minutes for questions.
Good morning to all. I'm Francesco De Franco. I'm the assistant chief of Mr. Ciccolella, that is the manager of the protected area. We are the managers of the marine protected area and the natural terrestrial reserve of Torre Guerceto, that is in the province of Brindisi. We are included in a larger system, that is the system of Italian MPAs, that are that we have 27 MPAs in Italy and 2 underwater areas, and we protect more than 200,000 of hectares of sea and more than 700 of coastline. But the system are in improving, so we have other 17 upcoming MPAs, and you can see that the distribution of the MPAs is in all the coastline of the Italy. We are a management body established in 2000 and formed by the 2 municipalities, the Convegno and Brindisi municipality, and the NGO WWF Italy. We are here in the north part of the province of Brindisi. Torre Guaceto is a really complex system because we have different level of protection in an area that is not really large, because we have 2,000 of hectares of protected sea and 1,000 of hectares of protected land. But in this we are a medium. We have a medium extensions for protected area, but in this area we have a different level of protection, because we are a marine protected area, a natural terrestrial protected area, but also a site of community importance for the Habitat Directive and a special protected area for the Birds Directive of European Union. And really difficult in the management is the boundaries of the different protected areas is not overlapped perfectly, but we have different section with no protection or a different level of protection. So we're trying during these years to have only one protected area with only one boundaries, in order to have a more effectiveness in the management. And as you can see the zonation of the marine protected area. Consider that all the MPA Italian system is the first attempt to planning something on the sea for the Italian. Consider that we started to have marine protected areas until the 1979. That is the first law for the protection of the sea, and in this law we have a list of marine protected areas to be established. With the institution of the protected area, we have also the zonation. That is a limit for the manager, because in the institution decree, that is a real important law, we have also the differentiation of the area in parts with different activities allowed. This is a limit because we can have an effective management if we need to change the level of protection in different areas. So we have okay, the red zone is the no-take zone. It is with no human activities allowed within these boundaries. This is the general reserve, in yellow, with only touristic activities allowed, like bathing or diving. And this is the Zone C, the partial reserve, where it is allowed to have some professional activities like the artisanal fisheries. So this type of different level of protection is written in the institutional decree. So to change this zonation, we need to have difficult phases, procedures, and it's very dangerous to modify the institutional decree. So we have this limit is common for the Italian system. It is not the best practice to have a management of a protected area. I talked before that we have different level of protection because in this area we protect a high value of biodiversity. This high value of biodiversity is was recognized by the RACSPA, that is the international organization for the Convention of Barcelona for the protection of the Mediterranean Sea. We are included in the SPAMI list, that is the special protected marine areas for the biodiversity in Mediterranean Sea. For two type of habitats really relevant, the coralligenous formation and the Posidonia medius. Consider this map. In red there is the Posidonia medius, and here we have the no-take zone. So the most important habitat for the marine protected area is out of the high level of protection area. We studied very hard our marine protected area, making in a period of 10 years a really deep scientific monitoring, and we studied this area in order to have a planning for the management. And you can see only a scheme for our procedures of management, so the study of the area, the stakeholders' involvement, and the guidelines for the conservation, but also the monitoring that helps to have an effectiveness in the management. And it is a conceptual model that describes our area in order to the biodiversity target for the management, the direct threats, and the strategies made to face the direct threats. We only focus on I only to focus in two important direct threats for the marine protected area and for the marine habitats. That is, one is the sedimentation. That affects the assemblage of the fish assemblage, the bentonic and the coralligenous, all the marine assemblage. But I talked yesterday in order to prepare this presentation with organizers, and considering the monitoring of the sea, the treat of the sedimentation is one of the most important for us, because we need to we started to study and to analyze the wave models and of the marine protected areas in order to see the origin of this sedimentation, and we see that probably we have an important phenomenon of coastal erosion in the south part of the marine protected area, and dominant currents and winds take this material and bring it in the north. An effect is to have a system in the zone A, so in the high value protection area. We have a problem with a high level of sedimentation, and this high level is saturated the bay, the lagoon. So now we are trying to study this problem in order to plan some action to face this directly. So I complete.
Thank you. Thank you very much. First of all, can I ask your name again?
Francesco De Franco.
Not Ciccolella. I also was wrong, and the program is wrong because yes. Ciccolella couldn't come, so you are yes. taking. Thank you very much, Francesco. Any question? That's a pity because I had one.
You made the point that the present zonation of the protected area may represent an issue for the proper management of the area.
Yes.
So I deduced that such zonation was not realized by environmental managers in the past. So my question is, what about current legislation on the marine protected areas? If environmental managers are now due to be involved in the zonation, or if this is an option?
No, the problem is not if the environmental managers are involved or not, because all the marine protected areas was made after a study, a technical study, in order to decide the boundaries and the zonation. The problem is that the Italian legislation wants to have the zonation in the institutional decree. So the zonation is not a decision of the manager, of the practitioner, but is a decision of the legislation level. So the problem is that it's very difficult to change this zonation, but the problem is that the law is described in the decree the zonation. So we need to change this type of approach, because for the terrestrial area the approach is correct, because the zonation is the final step of management plan. So we have a management plan during with a period of 5 years, and we have a zonation for these 5 years. In the marine protected area, no, because we don't have a system with the management plans. Now we are starting to have this type of system, and the zonation is not the result of the studies, but is only the starting point of the management.
Thank you, Francesco. So I will sacrifice my question and leave the floor to Matteo Tirindelli da Polonia.
Yeah, I'm sorry we are running out of time. I then suggest that we take our lunch break
after Matteo. I kindly ask you to try to stay on time, also to provide short answer and questions. But we will have time later on to recover because we are already discussing, and then there is 1.5 hours allocated for the working group. So we will try to speed a little bit in the afternoon. So just be patient, and then we will have our lunch break. Thank you.
Avanti, indietro.
Okay, thank you, Jacopo, and thanks for CMCC for inviting me. My name is Matteo Tirindelli, and I work for Da Polonia. That is a consulting engineering firm based in Genova. Da Polonia basically covers a broad spectrum of engineering sectors, and among these broad span, we have a oceanography and marine modeling unit. I joined this unit a few months ago, like in December of 2013. My background is more as a coastal engineer, and now I'm working for an oceanography and marine modeling team. So I think that the term applied oceanography or operational oceanography is actually something that really fits my background. I'm going to talk about the use of metocean data for maritime project application, especially for transport at sea. So I'm basically going to approach my talk from the point of view of the end users, of the engineer or the metocean consultant, and try to do the best use of all these databases and forecasts and data that are available at present that have been described in the previous talks. So it's very interesting for me. We are not researchers, we are end users, but we need to make the best use of what you guys are producing. So you probably know better than I do that metocean data for transport in the sea, and especially in the Mediterranean Sea, is a hot topic at present. Between 2013 and 2015, actually, a series of 16 huge lock gates, 4,000 tons each, and transported by heavy lift vessels, are going to be moved from Trieste all the way to the Panama Gate. And so part of this transportation is going to occur in the Mediterranean Sea, is actually already occurring as we speak. So the topic is really like hot, as we can say, as of now. The outline of my presentation, I'm just going to provide a brief introduction of the topics, and then I'm going to present two case studies, two projects that my colleagues at Da Polonia have been working for in the past few years. And I chose these two projects. We actually do a lot of metocean analysis for transport at sea. We were also involved in the Costa Concordia project, and actually we are heavily involved as we speak now for the Costa Concordia project. Both are metocean unit, but also the environmental units and the structural civil engineers. But I chose these two projects, one based in the Mediterranean Sea and one based in Indonesia, because those were two similar topics, but two very different projects in terms of timeline, budget, data availability, and needs from the client. So we took two very different approaches for the first and the second case study. And obviously, if we were in a perfect world, we will always choose the best data. We will take a long time to do our fine and high detail analysis, but sometimes we can't. And more often than not, we can, because the project has its timeline, its budget, its needs. So with two very different approaches, I'm gonna show you how we can produce quality for the client in terms of metocean analysis. So metocean data are very important for transport at sea. You know that there's a lot of different meteorological and metocean institutions that are providing databases all over the world, and especially in the Mediterranean Sea. These databases, as you've seen this morning, and as you will keep on seeing in the next couple of days, are very diverse and very variable among each other. The variability consists in the length of the database, the type, the accuracy, the time step, the spatial resolution, and I wanted to add a voice that is very important for the consulting company, for the end user, which is the cost. Some of these databases are, thanks to university and institutions like the ones that we saw this morning, are are free and are freely available and they can be used, but high quality data, often they cost money, and so the project, the end users has to cope with this constraint and budget. So there's always the need to cope and to compromise between the quality of the product and the needs of the project. The first project that I'm talking about, Meteocean study for transport of the yoke. So the yoke is this yellow structure here, which weighs about 550 tons, and it connects a ship which is called the Leonis, which in 2008 was permanently moored in the Vega oil field. The Vega oil field is in the south of Sicily. It's an oil field where Edison has one platform for extraction of oil, and in 2008 it was decided to permanently moor this vessel to become like a storage tanker for the oil field. And so we were asked by our client to provide a Meteocean analysis along the ship route, because the yoke was being built in Punta Cunio over here, and then it was transported about 70 nautical miles all the way to the project site. So what were we asked by the client, and what did we agree of providing as a product? We were asked to provide support to their planning operations for the transport of the yoke. So they asked us what are the best time during summer of 2008 for us to transport the yoke in order to have a safe transport and optimize maintenance and transport operations. We were very lucky for this project because at Apollonia we have been monitoring Meteocean parameters and measuring directly Meteocean and structural parameters at the Vega platform since the beginning of the 2000-2002. So we had already at the time about 6 or 7 years of data, measured data, high quality data. And the measuring system actually keeps on measuring as we speak now, and these data have been fully checked for quality, and we are proud to say that about 95% of the data are good data. So this is a percentage which is really high in the offshore industry. So on top of the measured data, our data, the Vega platform, we also had the luxury of using other data which are still measured in locations near the project site to do some sort of cross validations and calibrations. So what we provided to the client is a practical tool to support their decision making for the project. Another feature that we can provide at the Vega field, we know the site very well. We have tools to generate forecast of Meteocean parameters. We use usually, in this case, we use general databases for the Mediterranean Sea, which are available at a large scale, and then we nest our wave models to the large scale modeling forecast, and we take the waves to the project site for use to the specific project. Few pictures that show you where we are. This is the oil field, the Vega platform, and the FSO Leonis. This is the Vega platform. This is the ship moored with the yoke to the buoy. So the next slide, if you can help me, should be an animation that unfortunately doesn't run very well on a Mac computer, but we have a solution here. So why this is the Leonis, which is permanently moored to the buoy. You cannot see the yoke now because it's covered by the splash of the waves, but this was taken during the winter. It's a winter storm at the project site. I forgot what year we are talking about now, but stability of this structure is a real issue, and so maintenance operations, not only transport operations, but also maintenance operations are very important, and so the need to have very high quality Meteocean data is actually very important for this project. I think I'm running out of time, so I'm gonna... Come? No, va bene, va bene. Okay, so the practical tool that we provided to the client, we did a full Meteocean study. We also provided, results of our modeling efforts and everything, but what they were really interested in was some sort of tool that they could use to support their operations. So this table shows you that for different significant wave height classes, every 2 weeks during the summer of 2008, we provide the percentage of time that the waves are lower than a given operational threshold. So for example, let's say that the installation operation lasts 24 hours and that the client cannot operate with significant wave height larger than 0.5 meter, then they will choose this operational window here because they have the largest percentage of time that the waves are lower than 0.5 meter. Also, we gave them another table, which obviously this table seems simple, but they consist of a statistical analysis of a lot of very high quality data. So the installation operations last 24 hours. So this table here shows you that between two storms that overcome the threshold of 0.5 meters, on average there are 41 hours of waves lower than that. So the end user can plan their operation and know that on average they have 41 hours of time to do their maintenance and their installation. What if something goes wrong during installation? And for example, if during installation or maintenance the operation lasts 24 hours longer than planned, then we provide this table here that shows that basically helps them facing the risk. They know that there's 55% chance that the waves will be lower than 0.5 meter in the next 24 hours. So they can take their risk and they know what is the risk that they have to face. Another product that we produce for them is forecasts every 3 hours, waves and wind, with a warning system. These are bulletins that we provide every 3 hours to the client, and they can visually see really quick. If their threshold is 2 meters, they already know when this threshold is overcome. We produce these also in a graphical form for waves and wind, and also like a two-dimensional plot of significant wave height at the project site every 3 hours. Again, this is our wave model nested to the general forecast in the Mediterranean. The other projects, it's a very different location. We are talking about Indonesia, and the client needed to move to transport gas all the way from here to the island of Lombok. We are not in the Mediterranean Sea. We are in Indonesia. Lombok is a very high touristy area. As you can see, it's wonderful over there. But they have an electricity shortage problem, especially during the evening. The peak electricity demand in the evening is too high. And so, okay, I'm going to close now. Compressed natural gas was the solution, and the client asked us to analyze the meteorological situation at the loading and offloading sites. And the project was not even a feasibility study, it was a pre-feasibility study, so we didn't have budget, we didn't have time. And so what we did, we took some available information which is very rough. It's not fancy, nearly as fancy as you've seen this morning with all the databases, but that's what we had. And so we made the best use of this data. We provided wave climate and extreme waves offshore and near shore. We didn't even do any numerical modeling because we didn't have the budget. We transformed the wave to the project site with some analytical formulations, but we were able to provide this information to the client, and this helped the project move forward because they didn't find any risk given the meteorological situation, and so the project moved forward. The message, final message that I think is already clear from what I said, the compromise between high quality data and project needs is what drives meteorological consultants. So when we are lucky, we can do the best with the available data and with the best data, but when we are not, we need to make the best use of what is available out there. So sorry for being too long, and thank you for your attention.
Thank you. Thank you, Matteo. I think we have a very short time for a question if you do have. It's interesting because we had the academics first and now coming from the company side, from the perspective of private, so it's a very interesting session for me. Quick question. Wave periods.
Yes, wave periods in general for any kind of ship mooring project. They always ask for. We provide forecast of wave periods to Edison for this project. But yes, a significant wave height, wave period, currents. We can also do hydrodynamic modeling of currents for our forecast system.
Okay, thank you very much again to everybody. I think, Paolo, you can give the direction. Thank you.
The lunch is going to be served where we had the coffee break. I apologize
with Claudia Pizzigalli and Franco Reseghetti. I kindly ask you if we can postpone your talk after the lunch. And the lunch break is 1 hour. Please try to be back here on time so we have some chances to have some break before the dinner. Thank you.